What's up, guys? Tim Halston with DragBoss Garage. Welcome back to the channel. It's good to see everybody here. I can see we have a huge lineup of guests already. Let's see, nobody's here. Greg from Australia, The Shed, thank you for showing up. George, it's good to see you here. Fred Ebert, thank you for the help you've been giving me with that video that I got coming up. Keep that under your hat. Chris Palnick, good to see you from Canada. He's a Cleveland racer. Thank you for that, guys, being here. I want to thank my wife, Mrs. DragBoss, so make sure you check out her channel, and the bossettes, Elena and Izzy. Actually, they're inside. I had them get off the computer because I don't know if it's the weather, but we're having some issues with the computer. When Darin and I were working on this, he's got a presentation he's going to put up, and it was coming up all blue, and I started to have palpitations and chest pain because I'm like, okay, you know, I can fix bodies and hearts and do emergency room work in cars, but when it comes to computers, I'm not the king there. So it came through, and we're happy about that. I appreciate you guys. There's 22 people here already. So a lot of you guys were here before when I had Don Lacido on. Now he wanted me to tell you guys that he wants to do another live chat. So he wants to talk just about stories of where he did and what he did and how he did. And we'll leave it at that. So a long time, hey, Ed Case, good to see you. I'll tell you, over a year ago, I had talked to Darin. I said, hey, Darin, you know what I'd love to do a live chat on? Single plane intakes. You know, most of the guys that we talk to here run single plane intakes. And I always, you know, wanted to port one, and I have what I'm going to work on. And I'd like to get some tips on that and get some information. Well, we had talked about it. You had a lot of stuff going on, Darin. You told me, yeah, you better do this to the intake. So I would do what you told me to do. I'd take a picture, send it to you. Yeah, you need more work. Get this done. Okay, I'd change it or do whatever. So I kind of ported this intake and back to me with Darin's guidance on the phone back and forth. So we never got a chance to do a live chat on single plane intakes. And I texted him one day and I said, hey, why can't we just do a 10-minute, you know, live chat or half hour on single plane intakes? Ain't going to happen. And I said, well, what do you mean ain't going to happen? He goes, there's no way I can talk for a half hour, an hour on single plane intakes. That lecture series is a minimum of 2 hours, so I need 2 hours. I said, okay. There it is. It's glitching a little bit, so we'll just keep going. So I said, 2 hours, huh? I think we can afford 2 hours for all these subscribers. So you guys, make sure that you like the video, subscribe if you haven't. And like I tell you before, when Darin's on here, because he's taking time away from his family and his activities that he does. So anybody that sends super chats, this time I'm sending it all to Darin. I'm not putting any towards DragBoss Garage. Any super chat money goes to Darin, you know, to help pay for this, for his time to educate us. I think that's important. And anything that we make on this video, I give him half of it for the rest of the proceeds, because I want him to come back. You know, we were just talking about that, how good you are, Darin, to take time out of your family to help us, the subscribers here at DragBoss Garage, learn about intakes tonight and the importance of plenum volume in runner length. You know, now I don't know, he sent me some slides and said, oh yeah, Tim, look these slides over. And, you know, I said, well, I'll go print them out. Then I realized there's 60 slides, you know, and I'm like, my printer wasn't working. I go to Staples and then I couldn't print it down there. And I said, oh man. So we're ready to go. So with no further ado, welcome Darin Morgan, who works at BES, Bischoff Engine Services. So thank you, Darin.
Well, thanks. It takes me a while to put some of this together. It doesn't just come together instantly. So
without a doubt.
And this is something that is just like everything else, is changing rapidly. I mean, I spend part of my time, and everybody else in this industry does the same thing. I made a comment on Facebook the other day that continuing education is just part of the game now, because as far as material science and rapid prototyping technology and 3D printing and metallurgy and manufacturing process, it changes daily, it seems like. I mean, I almost can't keep up with it. It's like, 10 years ago, I wanted to tune EFI cars. Well, that shit's changing. I learned how to tune OEM stuff, and then the direct injection stuff came out, and I'm like, I don't have the time to keep devoting to that. I've got to do something. I've got to keep up with what I know. And what it does is it forces us all to specialize more and more and more into our individual categories, because the technologies that we can only absorb the new technology that's coming out within our individual career path. It used to be when my dad he built his car from the raw tube frame chassis, did his own body work, built his own engines, and fielded the car all by himself. Those days were done by the 1980s, and by 2000, you had to have a team of 5, each with their own individual specialty. It's still the same way. You've got your EFI guy, your touch guy, chassis guy, engine guy. Everybody specializes now. So I just kind of like to talk about my specialty, because most people never get to even see what I do. I am so happy you got to Lucido on too, because, there's some guys out there that are brilliant, like Lucido and other people that you never hear from. And I am so happy you are doing a series with him, because he is a wealth of information.
It's amazing. He's just, you start talking to him, you sit back, because he's got so much to say. Experience just comes out.
Lucido and we're both in the same situation. Lucido is the best kept secret for many teams. He couldn't talk about it. He could do heads. He was doing heads for the fastest guys out there, and like Pro Stock Truck and other people.
Yeah.
But nobody knew, because the people he was selling the heads to, he was verbally, at least contractually obligated not to tell people he was doing their heads.
Right.
Because if a team, if you're doing heads and intake for a team and they're kicking everyone's ass, the last thing they want is for you to give that technology to their competitors. So a lot of times they will pay you to keep your mouth shut and just do your work. And Lucido was one of those guys.
Yep. Because I asked him a couple of things. He says, listen, I can't even tell you now. I just can't talk about it. No. I said, well, I'm not going to tell anybody. He says, that doesn't work that way in my business. I just don't talk about it. And then I have to worry about it.
I can talk about
he said, I'm not
the generalities, the design, the basic design, the math, and all that stuff that goes into it. But who I work for, who we work for at BES, and what we do for those customers is completely, nobody will ever know.
That's the truth too, because when I was down there and I had my video, my camera, and I was filming, Tony said, Tim, don't even go over there. Don't even look over there. Stay on this side of the shop, and that's why it was, I'd ask him, I say, Tony, can I video this? Can I take some pictures of this? Yeah, don't worry about that, but stay out of that area. That's just how it is. It's still, secretive. It's,
well, it's not really a secret technology.
Yeah.
It's the work and the systematic improvement of the engine over time, or contractual agreements with engine companies that you're contractually obligated not to say that you do what you do. So, you're not going to lose a contract for engines because people find out that you're doing them.
Right. And it's something that you can't just tell someone about. Some of this stuff you really have to see, just like porting a head. He gave me a couple tips and told me to work on this and that. You can't really tell anybody how to do it. You just have to feel that grinder and just feel that motion and get the hang of it. It's not anything you read in a book. Oh yeah, hold the grinder upright, 90 degrees, move it to the left and right.
And everyone's technique is different. I've trained people for 30 years to do what I do. And some people can do it. Some people just can't. Some people take a little more time to achieve their technique, because everyone's technique is a little bit different. So it's like when a guy starts grinding and manipulating shapes and stuff, I just give it to him. I let him screw everything up and then backtrack. Like, this is what you should have done. So try that. And it takes 6 months to a year just for a guy to get his technique down to where he could actually do the job. this is not an easy task. I'm a grinding junkie, and I think Lucido is too. I could sit down at a grinding bench and 8 hours later look up and say, shit, I forgot lunch. I mean, it's just me. And professional head porters were almost all the same way. It's like it's just something that I picked up when I was 18 years old, and I just never put it down. I mean, I actually like grinding so much.
Put an earphone.
I don't even like going to the flow bench because it takes me away from the grinding bench. Let's put it that way.
Really?
Yeah. I mean, manipulating,
as
grinding,
long as it's not cast iron,
measuring, getting the design down on paper, and then and what's at my level, and people like Lucido and other people. I mean, we don't. When people say, well, you don't need a flow bench, you don't need a flow bench after 30, 40 years of doing this. I mean, you still do. Don't get me wrong. But as far as developing a port, the size, the shape, the angles, all that stuff, I mean, we've got that down. That's not difficult. I mean, I can do a port and go to the flow bench and hit 90% at 90% right off the bat because I've done it, 10,000, 25,000 times. I mean, it's not that it's almost muscle memory at this point. And after a while, we call it the flow zone or the grinding zone. You get into a zone and time will just vaporize. I mean, you'll turn around 6 hours later and be done with a manifold, and you're like, shit, it's 6 hours later. And it feels like 2. It seems like the harder you work and the faster you work, the faster time flies by.
You notice, though, I got to have music going. I put my little wireless. Man, I got some tunes going, and I can just, you get in that zone, and you just do it, man. Hear the music and just start seeing it. I don't even check stuff, you know. I'm
ADD.
See it. It just.
My subconscious brain is working off here, and I'm doing this. I know exactly what to do, where to go, how to grind it, but I have to have music in my ears all the time. Or actually, I don't listen to music. I listen to podcasts.
Okay. Probably listen to DragBoss Garage.
I listen to a lot of podcasts.
Right?
Yeah.
So I'll tell you right now, there's 51 people already. We've only been on the air for 12 minutes and 34 seconds. So that's going to be a good turnout, because I think most of the people that we have, my subscribers, not most, but a lot, they're all single plane type guys. You know, I mean, or single carburetor. There's a couple guys on here I see that have tunnel rams, you know, but that's probably a whole separate topic. Am I right? When you look at design.
Actually, we're going to go through that as well. We're going to go through the entire process of building the sheet metal manifold, from making the billet runners, the plates, how we put it together. And I wanted to do a presentation on single plane manifolds because the technology's changed so rapidly in the last 10 years. It's shocking. I mean, we can do things, you know, Chris Arachko does 3D printing of manifolds, and, you know, he can design this thing. We can say we need this RPM range, we need this plenum volume, yada, yada, yada. He can design it and cast a manifold that would have been completely impossible by any other means. You know, and there's a lot of rules out there now for cast manifolds. On the books, many sanctioning bodies have rules based around the fact that you have to have a cast manifold. Well, if that's is it a generally, well, in NHRA rules, it says generally available cast manifold. In other words, there had to have you had to have a manufacturing run of that manifold. Well, those days are long gone. I mean, Edelbrock doesn't make anything that these high performance can use. I mean, nobody makes anything that these ultra big engines can use. The decks are 11.5, 12 inches. I mean, nothing fits. So you have to design a cast manifold from scratch because nothing else will fit these things. I mean, we have ports, instead of down here off the deck, they're up here, you know, and they're aimed down. So, and they're this far apart instead of this far apart. So, I mean, everything is changed radically without 3D printing of the cores. And I'll go into that a little bit about how they do that as far as the 3D printing of the cores. Before, when you have a cope and drag, if you're going to cast something that has straight walls, it can't have straight walls.
Yeah.
It has to have what's called it has to have an angle in it. It's called draft in casting in the foundry.
Okay.
Because the core is solid sand. So if you make it straight, you can't pull it out. So it has to have a little bit of taper so you can pull this thing straight out. Well, that goes for everything. Water jackets. I'll show you some core boxes here. Water jackets, manifolds, the spider core in the manifold, that's all sand. So if you have two walls that are like this, you can't pull the core straight up out of there. You can't pull the thing apart. But with 3D printed cores, you don't have to pull it apart. So just print the whole thing and knock the sand out when you're done, and it's over.
Wow. That's crazy. I'd seen a guy named Jay Brown. You might not know him, but he's an FE guy. That guy builds and dynos FE engines. But I was looking up when I was doing this tunnel ram video. He actually took 3D printers and made tunnel rams out of 3D printing. Looks like plastic. And then he dynoed them, but they ended up blowing up on the dyno.
He was probably using a process called stereolithography. And what that is, it's a vat of liquid that solidifies with heat. And you have multiple converging lasers that come together, and they, blast a hot spot and just build up the surface, just like a modern 3D printer, but it's in liquid. And you can build manifolds. NASCAR did it for decades. They would make these stereolithographic manifolds, and it takes 24 to 48 hours to print a manifold, which isn't bad, but they would make them extra thick and then bolt them on the engine and run them, and then go make another prototype. And they would run these things through the motor, and that was their prototype development. And now you can literally print them out of plastic, which most plastics aren't strong enough to withhold the heat. I mean, that's the major problem. Right. Even they tried to run it, under hood temperatures alone will melt them. They're gone. Okay. But you can still dyno them. You can still try them. You can still proof your concept. So from that,
make them out of cores.
Nice. Those stereolithography machines were millions of dollars when they first came out.
Really?
And I think you can buy one for like $100,000 now. I mean, because everything's 3D printed. And now you can 3D print in aluminum, titanium, stainless, concrete. 3D printing is awesome. I never got into it.
Buy one.
I never got into the 3D print. I haven't bought a 3D printer. I don't want to, because I don't have the time for it. Yep. Because that is another career all its own. The amount of the learning curve with that it's not steep. It's just really long and drawn out, and there's a lot of failure rate as far as learning how to put it all together, and the temperature at which you do it, and the speed and all that stuff. And plus the CAD models that you have to import. Yeah, it's a whole other thing. I mean, I got into electronics, and I'm not an electrical engineer, and I have to measure these electronic circuits, which that's called metrology, when you measure stuff. I'm not a metrologist, so my learning curve was steep. I mean, and as far as on a learning curve with this stuff, I'm about right here. That's what I like about it. I mean, this stuff makes me feel exactly the way I used to when I first picked up a cylinder head and put it on a flow bench. When you're just completely ignorant, and everything you learn is something extremely new. It just feels so good to learn that new stuff. Oh, okay, to figure something out. And, electrical engineer would just go, but yeah, I wouldn't know that. I don't. I always
now you got a new microphone.
I feel most comfortable when I'm behind the 8 ball, when I'm underfunded, undertimed, and behind the 8 ball. That I feel perfectly comfortable in that situation. When somebody comes to me and says, I need a head in a week, and I need you to completely do this and this and this, and it's going to take a week, and I need it in 5 days, man, I'm there. I love it. I love
best work under pressure.
Yeah, the one thing I enjoy doing is repairing blown up shit. Because nitrous engines blow up. Shit happens. All right. I mean, people's are blow up engines all the time. But I like take a cylinder head that's missing 2 chambers, cracked all the way into the spark plug hole, weld that thing up completely, and air hammer it, remachine it, put all new seats and guides in it, new spark plug hole, and you can't tell I touched it. That's what I get off on. I really enjoy that, and not have to mill that head any more than about 10 thousandths. That's challenging, but it's when you're done and you hand that back to the customer and they're like, what chamber was blown up? I can't tell. It's like, all right, that puts a smile on my face. We about ready?
I was going to say to Todd, they may have heard this, but now you got a new toy, that microscope in the back.
Oh yeah, my.
You hear me?
I got this for a song. The stereo 2400 power stereo's telescope or microscope. I got this thing for $65, brand new in the box. I couldn't believe it.
Well, let me tell you something. Because now we got computer lag, so sorry guys. Not a lot I can do with that. But so let me tell you something. So here's $20 to help pay for that microscope from John Salvatera.
Thanks, man.
So thanks, John. We appreciate it. Darin guys. It says, hello, Tim and Darin. I have a single plane cast intake from CHI for their heads, 9.2 deck height. Grinder ready to go. What to do?
Not much.
That's a tough one to answer. And
that manifold is short enough to turn 9,000, 9,500 right off the bat. It's properly sized for a 400 cubic inch motor between 65 and 8,800 right out of the box. If you're going to push the RPMs up or you're going to put it on a larger engine, sometimes I'll have to put some epoxy in there and lengthen the runners because the RPM is a little lower. We'll talk about that here in a little bit. But that manifold is a really good manifold. I mean, we use that manifold on a lot of stuff.
I'm trying to think of that kid's name that had a Ford truck. Dustin. Anyways, he had a CHI headed that you did port work. Do you remember? You know what I'm talking about? Dustin made like 800 horse.
Dustin Rainey.
Yeah, that's him.
Yeah,
that's him. Yep.
All
right, there you go, John.
Didn't they just do that engine?
More tips in a little bit.
Didn't they just do that engine like 3 weeks?
No, that's been a long
time. Okay. Because I had an engine
the last
similar
time I knew
to
that thing was running was like.
I had an engine similar to that. It was 398 cubes with some C3 heads on it and a really good manifold. We took a CID manifold and cut it down. And they asked me how much. Well, the heads flowed 400, so I know it's not going to make any more than 920, 930. And I just said, well, it's got 960 lift. It'll make 900 horsepower. So it made 898 horsepower. I mean, it's not hard to predict how much power an engine will make. Just look at its limitations, count them up, and then that's going to tell you where it's going to come in on power and where it's going to come in RPM range. After 40 years of doing it, I can do that. I love. Your video stopped, by the way.
Of course.
I used to love trying to make predictions. Do the math, try to figure out a new combination, something I've never done before, and try to hit it within 10, 20 horsepower. And that's not a difficult thing to do anymore.
I use Dyno 2000. It seemed to work within 20 horsepower.
Simulators are awesome. I love simulators. The problem with simulators, I simulate the circuits that I build and manipulate the circuits.
Yeah.
But any simulator, it doesn't matter what simulator it is, it cannot ever, well, it cannot to date simulate real world conditions. There are too many variables outside of its scope to take into consideration. All it can do is do the math. That's all it's doing. Logarithmically going through all those calculations to try to arrive at a somewhat area of where this thing's going to end up. So designing something in a simulator, it's always good to use simulators. It gives you an idea of what makes what tick, what affects what. Trends, you're picking up trends like performance trends engine analyzer. He called it performance trends because that's what you're doing with a simulator. That's all you're doing. You add 2 degrees of duration and the engine picks up a little power and hurts torque. Now, is that what's actually going to happen in the real world, or is that the trend of actually putting 2 more degrees on that combination? See?
Yeah.
So when it comes to engine simulators, I always took an existing combination and then simulated that and then saw how close I was and then start making changes to the simulation. So I always worked backwards.
Okay.
You can't design an engine in a simulator unless you've got a lot of decades of experience, because an engine analyzer pro is really good in a couple of different ways, in a lot of ways actually. But in one way, you can either put the flow curve in there, or you can just use what's called a discharge coefficient, which is the average of that area and flow. So you can just play around. If you don't know the flow curves and stuff, you can just put that discharge coefficient in there and play around with that, and then baseline the simulation with the dyno, and then go back and forth. I've always found that if I baseline the simulation and go back to the dyno, that the trends follow. And that's all you're doing. You're picking up trends and seeing if they'll follow and mimic itself in the real world. You can design a circuit in a simulator, which I spend hours and hours and hours and hours on the weekends simulating the circuit, and then build it. Dude, it's so different. It's things in the real world have a lot of variance. You know, the math isn't finite. It's not exactly 200 ohms or 200 horsepower. It's 210.5. And okay, that's one variable that's a little skewed. And then you have 100 different variables with a little bit of skew in each of them, and you add all those up. Well, that's a lot of variance. Stack tolerance is what they call that. So you have to be careful with simulators, but they're fun and educational.
When you first start to design an intake,
do what?
When you first start to design an intake, you have to look at the package that you're doing it for, obviously.
Yes.
Right? I mean, are you looking at the RPM range more? Or you look at the cylinder head flow, a combination of each? How does it start out?
RPM range first. Okay. What is the operational RPM range of this engine? Because you only have 1500 to 2000 RPM in which to tune the standing wave and the amplitude of that wave and the harmonic, which we will talk about here in a little bit. It only lasts for 1500. In an EFI engine, it's 2000, because on a carbureted engine, you are relying on signal to pull that fuel out of the booster. With an EFI, you are putting the fuel in there regardless of the signal. So you can match the signal to the fuel. The signal doesn't have to be higher in order to pull the fuel. So what happens is the engine comes on the cam sooner, because you're not relying on that thing getting into the harmonic as fast, and it goes away a little smoother. So you've got 500 RPM on, almost 250 on both sides. So you have a 2000 RPM band. So I say, where do you want that band? Don't tell me 2000 to 7500. That's not the real world. Okay. That's circle track. That's endurance racing. That's not drag racing. You have 2000 RPM and really 1500. On a drag motor, you have 1500 RPM to work with. So the length of that runner is going to be dictated by where the operational RPM range is. Then we have the amount of valve area and how efficient that valve area is, which means how much air I can actually pass through the system. Then I have to figure out, okay, I need to hold at least 80 to 95% of one cylinder in this runner. So now I have length, I have volume, and I have flow rate. So now I can set my air speeds in the system.
Okay.
And that's it.
Let me put this question up here because it's kind of what we're talking about right now. So I don't want to miss this here because it kind of ties in. Turbine Research, okay, $4.99. It asks, what is your thought process to find performance gains when you look at a cylinder head that is completely unknown to you? Example, my 1987 six-cylinder 12-valve BMW.
Okay, the first thing I would do is find out what the intake valve size is and exhaust sizes. Then you have to quantify what the flow potential of that valve is. I mean, how much air can you pass? At what efficiency level you can pass that air? Then you can say, okay, well, I have this much air going, I can build this much airflow potential in the engine. That's going to dictate above all else how much power you're going to extract from it. So let's say you have your BMW has a 2200 intake valve. It doesn't, I know. But let's just say it has this huge exhaust, this huge intake valve. Well, the flow potential on that is 1,000 horsepower at 9,000 RPM. Way more than I'm expecting you're going to need down at 6,500 RPM. That's the opposite of what actually happens most of the time. Usually you have too little valve, too little airflow to reach the power and RPM potential that the customer requests. So at that point, I have to figure out all the limitations within the system. Can I manipulate this system, i.e. increase valve size, increase exhaust size, port size to reach the power potential or the goal the customer has for it? And once I do all the math and figure all that out, then I can go to the customer and say, okay, I know you wanted 820 horsepower, but I'm only going to be able to get you 750 because an OEM casting, you can only fit this much size. I can only get 80% efficiency. I can only get this much runner length, yada, yada, yada. That's how I do it. And
there is turbine research.
It almost always comes down to the potential of the valve. I mean, the valve is the cork on the bottle.
The limiting factor.
I mean,
the limiting
how much
factor.
air you can pass through that valve at a high efficiency is what limits the power. If you just go in there and blow the whole thing out and make it flow a ton of air up high, it's not going to make any power at all. You're going to lose power. The whole idea is to balance that flow potential and then raise the efficiency, meaning utilizing the area versus airspeed the best you possibly can. It's called the discharge coefficient. If you have a big hole flowing a little air, this discharge coefficient is very low. In other words, it's not utilizing that area to its highest potential. The other thing you have to quantify is what is the potential of that area? And that's not easy. A lot of times that's probably one of the most difficult things I do, because we're going to get off into things here, but the valve itself is the valve's potential flow versus its efficiency is really dictated by the initial design that somebody gives you. If you have an OEM cylinder head that has very low ports, the valve is sticking up and it's got a lot of angle and the valve port's real low, well, your efficiency is going to suffer. So now it's not the flow potential anymore that's limiting the engine. It's the efficiency of that port and of that valve that is limiting the power potential. And regardless of what it flows, you're not going to be able to utilize that flow because you can't get the airspeed up.
Well, think about this. What you're saying, when you look at the whole picture, you got to take in consideration the cylinder bore size. Who cares sometimes what that valve is? That bore is going to shroud and going to cause an issue. So you may benefit from going from a 220 down to a 208 intake, or 215. May flow less air, but pick up power because it's less valve shrouding, right?
Yes. And on another note, I'm going to show within this presentation port design, height, and how the efficiency changes. Because let's take, for instance, a 23-degree small block Chevy, okay? The absolute worst port ever designed by humans, period, okay? It comes in low, has to go up, then make a hard turn straight down, okay? So that instills what we call a velocity gradient, huge differences in airspeed. So what you do is you end up having to make that much bigger to get the flow potential up in order to turn those corners. In order to navigate those discharge coefficients, you have to make those areas larger. Your efficiency drops like a stone when you do that, because efficiency, the discharge coefficient, is flow versus area, utilizing that area to its highest potential. So if you have to make something bigger to navigate a corner, you just kill the efficiency. So therefore you kill the power potential and RPM range of the engine. No way around it. So if you look at pro stock engines, they raise the port. Well, the higher you raise that port to a point, the higher the discharge coefficient goes, because you can utilize that area at a higher airspeed and still maintain the flow potential. You're still getting high flow with a high airspeed. The power goes right up. You want to start the presentation?
See, this stuff I'll have to listen. Yeah, let's do it.
Okay.
These guys are getting antsy, and we got 90 people up here. I think it's a good time.
Go ahead and put it up.
I'll get up the slide here.
Okay, I've had this around for everything, for decades. And basically it shows what happens when that high amplitude pulse reaches the plenum. What you're looking at is the difference in airspeed and velocity of when the valve shuts, the pulse goes back out into the plenum, and it expands into the plenum, causes a negative reverses sign, and then comes in at the valve again.
Yep.
So this is basically what it looks like off of a sharp edge. Now, in the early 90s, we realized when we were trying to raise the RPM potential of the pro motors, we were still stuck with 55 millimeter cams. We didn't have the valve train technology to really do that. So we were brutalizing the valve train and doing other things that people don't have to worry about now in order to try to raise the RPM potential of that engine. But in doing so, we had to run the areas big, and we had to put a lot of taper in the runner. And we had to violate certain mathematical laws or general rules of thumb by doing that. And we increased the taper over and above what could normally be utilized in an engine like that. And what we learned was if we decrease the radius on the edges down to like from a ½ inch to a ¼ of an inch, it increased the efficiency, the discharge coefficient, and the signal to the carburetor instantly. We're talking 30 pounds an hour of fuel flow. We're not talking a little bit. We're talking huge gain in signal. And you're going to hear me use that nomenclature a lot. Signal. Signal is just the ability of the engine to transfer the energy and pressure drop of that valve up to that booster and move fuel into the engine. That's signal.
Got it.
So by putting those little radiuses on there, and by the way, we did this completely by accident. This wasn't engineered or designed. This is just trying shit and trying to find out what the hell worked. And that was mostly what we did back then anyway. And I'll show you the manifold grave pile. I built 21 manifolds in 1 year. That's all I was. Well, when I say I mean Garvey and the CNC guys and 3 other guys involved. We all built 21 manifolds in 1 year to run through our best engine to try to optimize the situation the best we could. And basically, at the time, I had seen a manifold like that. And then I did a manifold where my welds, I didn't get enough radius in the weld, and I was scared to go to a full ½ inch, so I backed off. And the signal was awesome. It gained like 15 pounds an hour of fuel. And I attributed that to the design of the runner and the angles. And then I went in and fixed my radius and the signal's gone. So I was like, uh-oh, it wasn't anything I did. I did it by accident. So let's just do that. Let's do that accident over and over again. So basically, this is what you're seeing is the air reversing. Now, the signal in the engine, the ability to pull fuel or move air and fuel through the engine is all right here. 50% of the game is right here. This is the cork on the bottle. This is the area that you have to make as efficient as possible. Otherwise, everything I'm going to talk about from here on out is a waste of time. So let's break it down a little bit here. So a lot of people will say, well, your inertia effect, an inertia effect is built off the wave action and the compression ratio volume factor. Okay. Without the compression ratio volume factor being high, without the wave action being of high amplitude and efficient, you can't build the inertia factor. Everything depends on everything else. If you fail in this chain of events anywhere, it affects everything after that chain of event. So, and I have heard this many times. The reason I want to show this graph is because people will say, oh, the wave, you know, the harmonics in the system are only 5% of the game. 5%? On a 2,000 horsepower engine, that's 100 horsepower. On a 1,000 horsepower engine, you're missing 50 horse. No, you're not missing 50. You're missing 120. Because that 50 you lost in the wave action kills another 50 on the inertia. Because if you can't get a high amplitude harmonic wave going into the system, you can't build the inertia. You can't get the acceleration of the air fuel mixture to feed the cylinder. So one depends on the other. You can't dissect these as individual entities and think, oh, I don't have to worry about that. It's only 5%. I've heard that about 10 times in my career, and I just cringed every time I heard it. So what is the compression ratio volume factor? Okay, well, I think it was, God, I can't believe I forgot his name. Alan Lockheed is the guy who coined the phrase port pressure lag in his equations, in his formulas for figuring out intake manifolds. And port pressure lag is simply, you can explain it like if you have a really small chamber and the valve opens, the air in that chamber, all those molecules react instantly. So let's say you're in a room 6 foot by 6 foot and you got a valve on the wall and it opens. The molecules of the air don't move, except it takes time for them to speed up to that valve. Okay, that's a lag. So big chambers, huge combustion chambers have what's called a port pressure lag. And this is another reason why small chambers on a normally aspirated engine instantly make torque and power. You're increasing your burn efficiency, your burn rate. And when you set that spark plug off, it doesn't have far to go, but the time it's completely burned everything. And when you open the valve, it's instantaneous pull on the intake. Bam. It sees signal right off the bat. So the bigger that chamber is, you've got that little bit of lag, which you can make up for, advance the cam a little bit, you know, to a certain extent. But if you have like a Hemi chamber with 100, 200 cc's in it, that lag is not going to be fixable. So any NA engine that you see will have, and you know, we strive for smaller and smaller, more efficient combustion chambers, and that's one of the 20 reasons we do that. The other thing is the wave action. Okay, the wave action, and we'll get into it here in a little bit. When that valve opens, all the air molecules, like a rubber band, start moving towards. It starts grabbing air up that runner. And pretty soon the signal moves right out to the opening of the runner and all the air rushes in to meet it. But before that, okay, if you hadn't set up a wave action, that's all that would happen. Well, when that valve shuts, it sets up a pulse that bounces back and forth. And you want to open that valve when that pressure, boom. And so you're initiating the intake charge. Right there, that's a huge advantage. You've just started everything off at a higher flow rate and a higher pressure. So now you've got this boost right off the bat, which does many things. You have overlap. This is during overlap too. So you're cleaning out the combustion chamber. You're getting the intake started as soon as possible. Because if you don't start it as soon as possible, you can't make it up later in the cycle. It's lost. It's gone. The whole idea is to get those molecules of air moving as fast as you can, as soon as you can. So now you've set up the wave action, and that wave is what starts this whole cycle. Let's just start there. That wave, that high amplitude pulse coming in when that valve opens to initially start that cycle and shove air into the cylinder is going to pay huge dividends when the valve is closing. Let's see here. This is the horsepower chain as derived by Patrick Hale in his Engine Pro manual. Right. And basically there's 4 cycles, okay? There's like 6, 7 phases. You have intake, exhaust, power, you know. Yep. Okay, 4 cycles, but you have phases in between there. I mean, intake pumping is a phase. Intake ramming, compression's a cycle. Fuel burning and expansion's a cycle. Exhaust blowdown is a phase. Exhaust pumping is a cycle. Valve overlap is a phase. So you have to go through cycles and phases. If any of those phases fail, power drops like a stone, because every phase affects the phase in front of it. So let's say you have poor overlap. In other words, your exhaust pumping or your exhaust blowdown. Let's take exhaust blowdown. In other words, somehow in the system you have too small a header or too short or too long, and your exhaust blowdown, which occurs before exhaust pumping. The exhaust blowdown phase is monumentally important because you're still opening under pressure. So the piston is not all the way down. I mean, you're dumping this thing when the piston's not even halfway down the cylinder. So there's a lot of residual pressure, heat and pressure, otherwise, i.e. energy. You have so much energy on the blowdown phase to capitalize on. That valve opens, it sees all that high pressure in the air, rushes out that exhaust. It immediately gives all that energy to that exhaust pipe. If your tuning is off, your sizing's off, your air speeds are off, you have a huge velocity gradient, you waste some of that energy. It turns into turbulence, it turns into noise, it turns into something else other than a pressure drop that you can utilize to help move air through the engine. Yep. So if you accent your exhaust blowdown phase, you have less work to do pumping it out, the exhaust pumping phase. And if you capitalize on your exhaust blowdown, you've got rid of most of it. So now you don't have the pumping losses of trying to shove it out. Free power right there. So let's say you have a perfect exhaust blowdown phase, perfect exhaust tuning and exhaust pumping. So on overlap, when the intake and exhaust valves are open, the intake signal, that inertia column that's coming behind there, can help clean that out. It can go right out the intake and exhaust. Cleans out, and also cleaning out the exhaust side of the combustion chamber is an art form all of its own. We'd have to have a discussion on that. Yeah. Because that's always a polluted area. It's hard to get rid of that over there. There are certain things we can do to help that. But let's say your everything is tuned, the valve overlap. Well, what happens if you hurt the wave action in the manifold? At that point, let's say your wave action was bad, so now you're pumping, your inertia ram column is of a lower amplitude, so now that affects your overlap. So you don't get the whole column started. You don't move air through the engine. So now you have a polluted chamber and you're getting less in the cylinder. VE drops right there. And if your VE drops, you can't initiate a high wave, and you can't initiate a high wave amplitude, your intake ramming suffers. And if your intake ramming suffers, your compression, your VE, and everything else suffers. It's just this circle. And if anything in that circle is not tuned properly, the VE of the engine drops.
So those harmonics, those waves are actually pulling more air and fuel molecules with them. That it's like pulling it this way towards the valve, right?
We'll get to that.
Oh, okay. That's what I'm seeing. When you talk like this, in my head, I see this stuff. Maybe you guys do too. But I see the valves going up and down. I see the air and fuel coming in, and I can see it. I don't know. It's weird. Maybe I'm a weird kind of guy, but I can see this stuff happening in my brain as you're talking about it. So I can see those pulsations and that pulling those molecules with inertia. Let's get them in there.
Remember when I said that I only had a few GIFs in here that wouldn't play? This is a GIF that doesn't play. God damn it. As the wave propagates, see those little red dots?
Yeah, yeah.
Okay, that's a fuel particle. What happens to a boat on the ocean as the waves pass? Does the boat travel with the wave? No.
No.
The waves go past the boat. Yep. The boat goes up and down,
yep,
but it doesn't move. But a little bit, tiny little bit. These waves are just pressure waves. That's all it is. It's pressure bouncing back and forth. And all we're doing is tuning these waves to a certain harmonic. Now, this can get confusing depending on what engineer you're talking to, because in physics, as opposed to electrical engineering, as opposed to mechanical engineering, they count the fundamental difference. Some people will say the first harmonic, they count the fundamental frequency as the first harmonic. So you have to clarify this with people. What is a fundamental frequency? The fundamental frequency is the opening and closing of the valve. That's the initiator. That's where all this starts. The wave goes in, the wave comes out. Okay. The second harmonic, we utilize that on tunnel ram manifolds, sheet metal manifolds. The wave comes in, goes out, comes back, intake opens. The third harmonic was always utilized in single plane intakes for a very specific reason. You have all the runners coming together very closely into a common plenum. And when you do that, the signal or the reversion or rarefaction of the wave changing sign and coming back in gets messed up. And you can't utilize the second. So you utilize the third. And forever, we always put single plane manifolds on the third harmonic. And the fourth harmonic, it has so little energy that it's almost useless. We don't use the fourth harmonic for almost anything. The second and third are the ones that we use. Now, as you go up in harmonic, bouncing back and forth, timing that valve opening with that back and forth, each time the wave goes out and comes back in, it's of a little lower amplitude. So the second harmonic is of the highest amplitude you could utilize. The third harmonic is a little less strength, and the fourth harmonic is so low it's not even worth talking about. And the fourth harmonic is usually utilized in like supercharger manifolds because the runners are so short. You can utilize those in like a turbocharged or something manifold where you have packaging considerations. But even in a turbocharged engine, and I'm not talking about Roots or high helix superchargers, I'm talking about turbo or axial superchargers, you can utilize the second and third harmonic to your advantage a little bit. Not as much, because I'm getting off base here, but as you increase the charge density, you go 1, 2, 3 atmospheres more, the harmonic drops. So your RPM drops. Because the wave, what is this wave governed by? It's the speed of sound in whatever medium that you have, which is air and fuel mixture, 14.2 or 13 to 1 air fuel mixture. So the wave speed, I think, is anywhere between 1185 and 1200 feet per second. So if you know your wave speed and you know your length, you can calculate how long it takes to go back and forth to coincide with the valve opening in 12, 15 milliseconds later. That's all we're doing. It's simple math, and it's not even You don't even have to know anything but adding, subtraction, division, really.
But how do you find this? I mean, you're not going to see this with the naked eye. You're not going to use lasers. I mean, how do you know these harmonics are there? How do they discover this? How do they put smoke in there? I mean, how do they see this? Where's this theory? Is it theory? Is it?
Well, at Rare Morrison, before I got there, and Lockheed and Edelbrock and others set up what is called a manometer spectrum. Okay. You had a series of manometers.
Yep.
Just like on a flow bench.
Nope, I get it.
And all the way down the runner, you had plugs separated by 1 inch. So those manometers would show the standing wave in the system. And as the RPMs increase, that standing wave would move forward.
Okay.
The amplitude of the frequency would be set and it would move forward. So you could actually visualize it that way back then. Back in the late 70s, mid 80s, they were doing that.
Wow. Okay, I got it.
So this is another GIF that won't play. But basically, this is the fundamental frequency. In other words, the valve opens, the air goes in, shuts, the pressure wave comes back out. Okay? During this period of time, as the wave is traveling out, you have the power stroke, exhaust stroke, other things are going on. So we utilize this one. By the time this wave comes in and goes out and comes back in, the valve's ready to open again. I wish these would play, but okay. Optimum runner length. Okay, this is on the second harmonic. Okay, so which is the most powerful one we can use, which is the one we utilize in all this, the manifolds that we can build this way, because it is the most powerful. And this is from Swartz Racing. You can go on his website at Swartz, and this is on there. I copied it off and put it up here. So basically, if you just follow the green line at 12,000 RPM over, you'll find that you need an 8-inch long runner. That doesn't change. At 13:1 air-fuel ratio, at sea level density, it's always going to be 8 inches. So this is a cheat sheet. Now, if you change your air-fuel ratio, if you change your altitude, if you change other things, will that runner length be affected? Yeah, but it's only about 200 thousandths either way. And by the way, it's about 100 thousandths per 100 RPM. You can think of it like that too. So let's say if your runner is 500 RPM shorter than it should be, you just add a ½ inch and boom, you're there. So this is probably the easiest thing to quantify when it comes to manifolds, the length itself, because it's the sound velocity in the medium and the length. That's it. If you know how fast it's going, you can dictate the time in which that travels back and forth to correlate that with the valve opening. And this is just a cheat sheet. So if you're going to run at 7,000 RPM, you follow that line over, it needs to be 14 inches. And where is that measured from? It's measured from the valve seat to the plenum entrance, where you have an area change, or where you have an area change that is twice the diameter or larger. So if you have a 2-inch pipe and it sees a 4-inch diameter pipe, that harmonic will tune up. In other words, when the pulse sees that area, it will turn around, turn sine, and go back in again. It'll send subharmonics up the runner if it goes out. But the whole point is, once it sees twice the area, it thinks it's seeing atmosphere. It doesn't know the difference.
Now, were they contributing to reversion in the intake?
Reversion is caused by so many things: lack of signal, lack of airspeed, low valve efficiency, so many things. But yes, if you have a runner that is out of tune,
right,
meaning its length. See, the thing is you can open the valve in a negative harmonic. So if you, let's say you tune the engine to 7,000 with a 14-inch long runner, as dictated here on this graph, and you're running the engine, let's say at 9,000 RPM with that, At that point, instead of being on the positive side of that, you're on the negative. You're on the negative side. So the air in the cylinder tries to go back out.
Okay.
Yeah, you have to, and we'll get into that. I've got some graphs here in a second that'll show why we do it that way, and this is it. So I've erased a lot of stuff on here. So let's just concentrate on intake valve opening and intake valve closing. And I drew in red down there, that little red hump down there under the intake, that's velocity.
Okay.
And I just drew that in there. It might not be exactly right, but the whole idea here, let's look at overlap between intake valve opening and intake valve closing. Let me see here if I got one. No, I took it out. You have overlap. And overlap is a negative harmonic on the exhaust that coincides with a positive harmonic on the intake. So you tune the exhaust side to come in with a negative pulse, and the intake comes in with the positive. So that means you move air through the engine. It's easier to move that air through during overlap. If during this period you are too short or too long on your runner, or too short, too long, too small, wrong headers on the engine, this is where you can get reversion. And this is, overlap reversion is very small compared to late or intake valve closing reversion, which is the worst. So let's say you have a positive harmonic, you've used all that energy, and now you're supposed to shut the valve, but the pressure starts dropping and you're holding the valve open, the air's going to go.
Yep.
Yeah. And if you have, during overlap, if you have overlap reversion, it's pretty easy to see because on the intake port will be black. You'll see, and the amount of black or carbon up that intake tract is proportional to the amount of reversion you're seeing on the overlap. And super gas, super street cars will always have black intake manifolds. And some nitrous engines will too, because of their cam timing. They're designed to run on the nitrous. So NA, they're going to revert like crazy and throw carbon and soot up the intake runner, which just turns it black. The extent of that black tells you how much reversion you have. If the black is only like 1/4 of an inch up the intake seat, you're probably fine. It shouldn't be that way. It should be completely clean. The intake manifold or the intake runner itself should never have soot or black in it. But if you've got 1 inch or 2 inches of black going into the bowl area and up the short side, you got major problems. There's a lot of power on the table you need to fix. So what we're looking at, that line that dips down and then comes back up, the pressure is dropping. That's cylinder pressure. The cylinder pressure is dropping. The piston's dropping in the bore. Okay. And during overlap, the negative and positives come together to move air through the cylinder. And then the intake, the piston starts dropping, the pressure differential increases, and the airspeed in the runner starts coming up, 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 up. Now the piston at bottom dead center, the intake valve is opening or closing at this point, but the air, now you have built so much airspeed in that system that even though the piston's coming up that bore, the air is still ramming in, still ramming in. You're exchanging the velocity for pressure at that point. That's the name of the game. Get the airspeed and efficiency as high as you can and exchange that later on in the cycle for cylinder fill. This is where 124 VE come from. This is how you can shove 20% more in a cylinder, a normally aspirated engine, than what it could otherwise do. You're using the harmonics, the overlap, and the inertia all together to accomplish that task. And you can't separate one from the other. They all work together. So as you see that the piston comes around, the pressure rises, But right in there,
Yep.
okay, right in that area, this is the inertia. This is the air slowing down, but the pressure rising. As it comes in, it's slowing down, but it's got all those molecules of air behind it, forcing it forward into the cylinder. The piston's coming way up. I mean, the piston's halfway up the bore. So the pressure's rising in the cylinder, and now you have this inertia coming in, counteracting it. These two things are working against each other. And then the whole idea here is when the pressure, you're supposed to close that valve.
Yep.
You close the valve right before that pressure is below ambient, or at peak VE higher than ambient. You're actually closing the air higher than ambient pressure. You're trapping way more in that cylinder than what would have otherwise been possible without the harmonics and the inertia you have built from the airspeed. And this is why I've always said for decades, airspeed, airspeed, airspeed. It's the greatest equalizer there is. I mean, it is the one tuning aspect of the entire induction system that fixes more problems than anything else. And what do we do as head porters when we first start porting? I did it. Everyone does it. Make it bigger. A bigger hole will flow more air. And that's correct.
Yeah.
That just, it doesn't work in the running engine. Dynamically, that doesn't work. You have to match the airspeed and the efficiency of that valve as closely as you can. Get the airspeed up and be able to utilize that with a high efficiency. If your efficiency drops, the dynamic airspeed in the system drops with it. Regardless of what the flow bench tells you. The flow bench tells you got 400 CFM. Okay, that's good enough for 920 horsepower. Not a problem. So let's say that you have a 92% efficient port and in the intake tract. You will be able to make 920 or even 930 horsepower. Let's say you drop that to an 80. You just dropped to 880 horse. Let's say you drop that to 75%. You drop to 750 horsepower. I mean, it's not a small gain or a small loss. It's huge. So let's take a look at some ports and how to navigate them with manifolds. I mean, what we're doing with the manifold is we need to quantify the length. We need to quantify the volumetric increase, or what people call taper. Taper is not angle, by the way. We don't think of taper as angle. Taper is airspeed and area. The taper that we talk about is how much area can I gain and still not hurt the airspeed up here at the plenum to reduce my signal from the carburetor or atmosphere, period. If you need volume in a runner and you put too much taper in it, it just kills the whole thing, but you killed your average airspeed. That's what we're dealing with. We're dealing with localized velocities that have to be a certain amount. Like the push rod needs to be 300. The short side needs to be 350, 380. The throat needs to be as close to 136 CFM per square inch of valve radius as we can get it. And if we don't get those to those points, we lose efficiency. So we can't capitalize on the flow potential at all. And that's the problem people have when they first start porting heads. I did, everybody did. It's like, get on that flow bench and you start praying to those damn numbers. It's like Maskin said it best. Richard Maskin gave me the best advice I ever had as a head porter. When I asked him, I was 26 years old, I asked him, on a high lift cam, let's say back then the high lift cam was 960 lift. Where do you want the port to flow? I mean, should it flow more down low in the mid-range or the mid-range and up high? And he goes, that's a stupid question. It should flow everywhere. And he's right. And you can do that. I just didn't know at the time you could actually do that. You can get the best of both worlds, but it's not an easy proposition. I mean, I could talk for days just on shape and how the venturi comes in and the bowl comes in and how we accelerate the air and match the back angles and the chamber layback and all that to open that valve and see a pressure gradient perfect out that valve and I could talk for days on that alone. But it took me 2 decades to realize what was actually going on. It really did.
Wow.
And when you have ports that are inefficient by design, and you are looking at a port that is, quote, inefficient by design, and this is indicative of like a 23-degree small block Chevy.
Okay.
So the airspeed comes in, and now you look at all these area changes, directional changes, and you notice how it has to bow out really big because the valve, the port is so high, it has to converge to the short side together. And now that makes the port narrow because you got to get around the push rod. So what you're doing here is you are inducing gradients, differences in velocity into the system. All the air wants to choose a straight line. It takes the path of a straight line, whether you want it to or not. So the air is going to start at the roof, go over the tip of the short side and across straight into the bore. That's what it's going to do. That's where the highest velocities are. The roof, the apex of that little short turn down there, and the back of the bowl. It's a straight line. Air doesn't want to turn, doesn't like to turn, and when you make it turn, you lose efficiency. But in order to make this port flow, get its flow potential high, because of all these gradients, differences in velocity, you have to make the areas in which this air has to navigate bigger than would be otherwise necessary to do that. So now you have like a big block Chevy port. It's a little better. It's a little higher. It doesn't have as much gradient. And if you look at the older heads, like the standard 360 Dart or any 23-degree head you can buy off the shelf versus a 20-degree, what makes that 20-degree so powerful? Where's that 80 to 100 horsepower coming from? If you take two heads, and I've done it many times, a 23-degree with a low port that flows 500 CFM, and you put a 20-degree head, same valve size, same basic chamber, except a little smaller, and make it flow 500 CFM, there's 80 horsepower difference because making those areas bigger than would have been otherwise necessary makes the efficiency nosedive, and you can't capitalize. You can't accelerate the air to a high enough to capitalize on the inertia. You can't exchange those two things later on in the cycle to fill the cylinder. So it limits your power and it limits your RPM potential. You can't wind the engine up as high, and you can't feed the engine as much. So your VE's lower and your RPM's lower. So now you go to a high port. And what is a high port? Oh boy. A high port is a port that is high enough, its opening is high enough to put its velocity, its highest velocity in the middle of that port. If you lower it like a 23-degree small block Chevy, all the airspeed's on the roof, leaving the floor completely dead. Huge gradient. You have 380 feet per second on the roof and 150 on the floor. Now, what happens if I raise that port to where that's right in the middle? Perfect. What happens if I raise it too high? I just instilled another gradient. I just put all the velocity on the floor, which is the hardest place in the world to navigate because you're trying to turn it into the high port heads. High port means you put it right in the middle. Raising it over and above that is a recipe for disaster. Let me point out there was an individual who shall go nameless who had no experience with cylinder heads, was a machinist. He didn't know the first thing about induction system design, manifold tuning, or anything else. Decided that he was going to do a set of billet heads. And what he did was, and by the way, we're still dealing with the same valve. He couldn't increase the valve area. So he was stuck on power potential right there. That valve's only going to flow so much. You're only going to make so much power, and you're only going to hit such a certain RPM with that much area, period. Can't get around that. So in his head, he thought, if I raise that port up straight, I'm going to get a lot better flow path. So what he did is instead of the ports being down here, he raised them up here. Well, now the manifold had a bow in it. He actually hooked the manifold. So he instilled another gradient upstream. So that engine versus a standard set of heads. Now you got to remember the guy spent like 25, 30 grand on this. That's a huge project.
Yeah.
And that engine over a set of cylinder heads that you can buy off the shelf makes 120 horsepower less. So it completely, and by the way, when I say this guy, I've seen this like 5 times in my life.
Okay.
It's like if I was going to build something, if I was going to build a chassis, the last thing I would do is just try to do it myself. I'm going to go to mechanics. I'm going to go to people that know what they're doing to tell me what to do, you know? And anytime I venture out on my own, I fail. I mean, it's not a mystery. If I try to go do something I've never done before, I am going to fail. It's a 100% certain. So what looks aerodynamic, what looks swoopy, what looks nice going doesn't work in the running engine and never has. It just doesn't. Because you're navigating so many other variables and counteracting things with that shape and angle and height. And what I'm trying to get is not as easy as just looking at it and thinking, oh, if I just make it line of sight, everything's going to work out. Line of sight is a good idea. That's something you should strive for. In other words, looking down the runner and seeing the most valve you can when that's applicable to what you're doing. Because when you have a perfect line of sight, you have a very, very high RPM engine. And as you turn that runner around, the RPM drops. So the short side itself, what looks like something that's in the way is what actually turns the fuel. If you don't get enough pressure drop at the short side apex, the fuel is just going to keep going and slam into the back wall, deatomize. Your burn rate's going to go down. Your efficiency is going to go down. Your power is going to go down. And chamber is going to be more detonation sensitive. That short side, the layback of that short side and the apex and the way that angle comes in on that runner is hyper critical to the way that engine functions. Because the more you stand it up, that's low end torque. That's all top end power. Somewhere in between is going to be the perfect tune-up for whatever RPM range, engine size, and what you're trying to do with it. So as a port designer, that's where we come in. That's where guys like Lucido and Matt and everybody, we look at, okay, well, what RPM potential is the engine? You have this much valve size, so you're only going to be able to run from 7 to 9,000, period. You're not going to be able to exceed that on this size engine. So what short side is going to tune up to that RPM range?
If I get it.
So here we have basically, did I show last? Yeah, that's like a pro stock runner. It's just high enough to where the airspeed's equal. If you notice, on the one in the upper left-hand corner, you see that the bowl has to be kicked out really, really hard. See, that's another velocity gradient. The air is not going to turn. If you think the air is going to turn around that corner, you're sadly mistaken. It's going to take a straight line to bore center, no matter what you do. So if it takes a straight line to bore center, what's happening to that area you just blew out in order to navigate that turn? It's going to be slow. So you initiate a gradient in the system, your efficiency drops. No way around it. This is like a 23 degree. Now, the ports are low because of packaging considerations. In the 60s, when this engine was developed, they had hood clearance issues. You had to fit a manifold that was very low. So this was perfect. This was an awesome design. There's nothing wrong with that. For the purpose in which it was designed for, couldn't have done better. But now you try to put a straight runner on there and wind it up, ain't gonna work. Now your runners are converging. The port is so low, and they're so far apart that by the time you put enough runner length on there, they're intersecting. And this is where you saw the cross ram manifolds of the 60s and the 70s and the Mopars and some of the second harmonic manifolds that were
Spread
over
out.
the valve covers way out there with two carburetors 4 feet apart, you know?
Yep.
I mean, if you think about to reach 7,000, you have a 14-inch runner from the valve to, shit, I can't even fit it in the screen. 14 inches is a long length. Now tune that at 2,500. Well, now you have 38, 40 inches.
Okay.
How are you going to fit that under the hood? The Mopar guys did a good job, though. This is indicative of like a pro stock head or a high-end, efficient head. And when I say pro stock head, I mean there are CID small block Ford heads, Macklemore's Assassin head, the RCV1 head from Jody Gunter. There are tons of heads out here that are like pro stock heads from the 90s or actually 2000s, the early 2000s. I mean, if we would have had those heads back then, oh, shit, we would have been world champions. That's how good they are. That's how good aftermarket heads are now. And when I say pro stock heads, it's kind of a misnomer anymore because technology's reached a point where you can go out and buy a head that's 90, 92% efficient just right off the bat. Not a problem. I mean, to buy a cylinder head, you can bolt on a 400 cubic inch motor, make 1,100 horsepower at 10,000 RPM without touching the damn thing. I mean, come on. That was a pipe dream in the 90s and the 2000s. The aftermarket, 3D printing, materials, science, rapid prototyping has made this world so much easier. In the 80s and 90s, in the 80s, you couldn't get your hands on what they were doing. In the 90s, you might get a trickle down effect of maybe 10 years later, you would see it. In the 2000s, it was 6, 7 years. Now, what you see, you can produce within 6 months. Easy. Runners, the runner on the manifold is just a continuation of the port. And the whole idea, all the job of moving the air is done down at the valve and in the bowl area and the short side. That's 65% of the whole game is accomplished down there. The runner is just designed to tune the RPM range as far as length and tune the average cross-sectional area or average airspeed of the system and the volume ratio to one cylinder. So if you look at it, the runner is a continuation or extension of the port. And we want to extend that port in such a way that we don't instill any gradients, any differences in velocity, any difference of direction. We want to continue that straight out. The port to the right is violating one of the rules that we try to never violate. The straight wall to the right on the port is what we refer to as the high-speed wall. That's bore center. So most of the airflow is going to be on that wall. So the last thing you want to do is change direction on the highest speed wall in the system. So you see that wall comes out and then changes direction. It's like putting a tapered port just straight on it instead of matching one of the walls to that. So the one to the left matches that straight wall. That is a straight high-speed wall. The air doesn't have to do anything but flow right down that wall to bore center. And all your area gains are made off the push rod side, which is already the highest gradient side. So just put your volume gains over there. I didn't know this until I was 35. I'll be 59 in 2 days. I didn't know this till I was 35 when I was messing with manifolds, and we were building manifolds, and just trying stuff to see what worked, what affected what. And when we affected something, we tried to derive a theory as to what was going on, design an experiment to prove that theory, and go back and forth and try to isolate what variable was affecting that runner. And the shotgun method is appropriate as well in this area. The shotgun method is you just fire both barrels. In other words, you build 20 manifolds and run them across the engine, and try 20 cams and run them across the engine, and look at your data and try to figure out what direction to go. That was the Bob Glidden method.
Yeah.
It worked, but he had to work twice as hard to do it. And this way is, okay, we've gained enough knowledge over the years that we pretty much know what affects what. So once we learned this, then we had that high-speed wall straight, and all the volume gains were made off the push rod wall. The roof and that high-speed wall don't change direction. You match those. All the volume gains are made off of the floor, which already has a gradient, and the push rod. So that roof and that sidewall do not change ever.
It's funny that you said that, but Warren Johnson said the same thing when he was on for a live chat and talking to him in private. He said Bob was great, but he would work in all night doing 8 different setups of heads to do all this stuff, just like a shotgun approach, instead of looking at it mathematically and from a scientific approach, engineer approach.
He took a methodical shotgun method approach.
Yep,
in other words, he had a memory like a trap. He never forgot a goddamn thing. And when he tried something, he could take shit that he learned 6 months ago and go, wait a minute. 6 months ago, I did this, and this happened, and then this happened. Put those two together. And that's what won his 85th race, by the way.
Really?
Yeah, because I had built a manifold, and for the original Hemi heads, it killed 30 foot-pounds of torque and made 35 more horsepower and carried the power band out another 500 RPM. So then he's sitting there, he's like, shit, I wish I could use that. You know, it's like I can't change my gearing and everything to move everything up.
Yeah.
And, and then he was just like, wait a minute. Those heads made 25 more foot-pounds and 10 less horsepower. So if I put those on here with that manifold, and that's what he did. And he went, boom, number 3 qualifier and won his 85th race. That was his last race, by the way.
R.I.P. Bob.
See, he had a memory like a trap, and he worked like a dog. And he could try 3 things to your one. Where you're trying to take the scientific, methodical approach.
Yep.
He's running shit through the engine, and his mind is going 1,000,000 miles an hour. both ways.
Coffee.
You can't do that anymore. That approach is not something that would be competitive, but everything advances. I mean, this is a nitrous manifold and when I say I built, I mean me and Garvey and the CNC guys at Rare Morrison. Okay. So this is a design. This was my design, of course. I designed them, and then everybody gets together. We put our heads together. It takes a team to do anything, by the way. No one man can do everything. So this is a finished Pro Mod manifold from, I think, 2010 or so. And we're going to go through exactly what it takes to build one of these things. Now, you notice that the flange plates are all scalloped, so they're lightweight.
Yep.
And these are all runners that are cut out of a solid piece of billet. And this is what it starts out as, and this is what the runner ends up like.
Freaking beautiful.
This is the machining process. You do all 8 runners at once. You make custom caps to whatever the port entrance is, and then cut around it. And then flip it upside down on a custom template and a top cap and cut the outside. Or inside, I mean. Here's 2 different runners of different thickness, different shape. And the one thing, you gain power by doing this, by going to a billet runner, there's like a pro motor back then, there'd be 4, 5, 6 horsepower on the average doing this, because instead of bending the metal and forming it and then having those discrepancies in that shape, every single runner is identical in length and taper and shape and everything. So what that does is it tunes the whole system up just that little notch, and that's 4, 5, 6 horsepower on the average. And on one of those engines, that's a lot. You have improvements in overall power band, signal, and everything else.
One of the things I'll mention that I saw someone mention in here too, is that we're talking about right now, we're talking about one runner, one valve. But remember, there's 7 others that are doing this too, and it's hard to put all that together. I mean, it just amazes me.
Well, we'll talk about all the subharmonics in the system here in a little bit, because the runner tunes up, the plenum tunes up, other things tune up as well. So after I have welded the runners to the flange, which, see, this is the straight bar that I put them on and tack them. So it takes me a while to get them straight and the angle's perfect, because I have to cut the base perfectly at whatever angle I want that runner to be at. And this is a symmetrical head, so they're all at the same angle.
Yeah.
So Bruce Allen at Rare Morrison made a deal you could slide the runner in. So in other words, you cut the runner into a solid piece and then put it on a slide that changes the angle. So that way you could cut all the runners. You slip them in there and slide them across, and you're cutting them all at the same exact angle. So this lets me make sure that they're all tilted up at the same angle. They're cut at the same side angle. So you're within, 10, 20 thousandths everywhere. And then we machine off the tops. And this is a very loud machining operation. You notice the rubber bands around there? Yeah. That's to kill the harmonics in those. Those are trumpets. And when you machine them, they scream.
Really?
Everybody in the shop will not only have earplugs, but they'll have headphones on top of them, because they are loud. Without that rubber band on there, nobody can be in the shop. Now, when you're building a sheet metal manifold, as you weld, the welds constrict and warpage occurs. So that flange you see will actually pull up like this, because you're welding on the top of it and everything's constricting, so it warps. Okay. So what I used to do is put a 1/4 inch drill bit on the table and clamp it at each ends and pre-bow it after I tacked them, and then weld them. So when I released it, it released more straight than would have otherwise been. So I had to mill less. Also, you jack the heads up on the block 120 to 150 thousandths. In other words, you just throw 260 thousandths gaskets underneath there of whatever deck height and gasket height that you have. Put 2 more gaskets on there, because after you weld everything together, the flanges are going to pull in 60 and drop 60. So you're going to have to mill 120 off to get it to set right. So all you're doing by putting those gaskets in there is you're setting everything up higher. So when that thing warps out, you can machine it back down. And you have to take that length that you lose into consideration on the final product. And there's the runners all welded to the flanges with the base plate you see down there welded on. As you weld that base plate, the runners are like this. And as you weld, those runners will pull in on the bottom. And that's what we call base warpage. It pulls in about 60 thousandths. So now your intake flange is like this, and it pulls in. So now the bottom is up here. And as you weld the plenum, it'll drop. So that's what you're making up with that extra 160. Sometimes you need 180. Depends on the thickness of the manifold, the rod you're using. I mean, how much weld you have to do. This is a manifold plenum. Usually I could bend them up on a break within, 25, 30 minutes. I mean, once I got them drawn out, bending a plenum is easy. You notice that those holes are, I use a hole saw what I'll do is I'll put the plenum on there and then trace around the outside of the runners and then use a hole saw to go in and drill those holes out. And let's go back, if you weld that plenum on like that, the amount of warpage that's going to occur is almost unmanageable. All these ends here will pull down and warp the whole thing side to side. So what you do is you drill these holes in there, and as you weld around that runner, the welding, the warpage and distortion goes down by about 50%. And it's a lot easier to get an accurate manifold that way. As you see, this is just tacked.
Yeah.
In other words, it's just tacked on everywhere. And you see the top rail is held by clamps. That's all tacked together. Everything is tacked together. And we bolt the manifold down and don't release it until we're done. And I usually let the manifold set for 10 to 12 hours before I release it, because I want that distortion to kind of settle, because I can save 20 thousandths, 25 thousandths of milling on that flange by just letting the distortion settle for 24 hours even. Just don't touch it. This is a inspection plate in the bottom of the manifold. Nitrous manifolds do this a lot because you have to go down into the valley on these things. This is 1 year of manifold development at Rare Morrison for a pro stock team. And you have to remember, at this time we had 13 engines in rotation, 4 rental customers at $25,000 a race, and we had 10 guys keeping up with those 13 engines in rotation and spares. That included spares. So for those 4 teams, there's 5 teams, including us, and every team had a spare in the trailer. So at the beginning of the race, we wheel the engine over in the spare, and they would race, and then they wheel them back at the end of the day, and you take them home. Now, this is just development, just picking up trends. Okay, let's try a little different. Let's try a little different runnering. Let's try a little different skew. Let's try a little different taper. And that's called the manifold graveyard. Those manifolds are scrap metal. They're not good for anything other than that one engine. Wow. They won't fit anyone else's engines. They won't fit any other pro stock engine, just ours. So let's talk a little bit about 3D printed cores. What has revolutionized single plane manifold development. What used to cost the customer $4,500 to $6,500 to modify an existing manifold, you can now spend $6,500 to custom design and manufacture a manifold specific for that combination that is better than any modified manifold I could ever do. And the reason is 3D printing cores allows for a huge latitude in design, where you have an original design, you have the pattern, and then you have the mold. You pour the aluminum in the mold. The thing about this is that mold has to come apart. And it has to be structurally sound in order to be pulled apart. And it has to have what's called draft. In other words, you can't have 2 converging walls or you won't be able to pull the thing apart. So the design itself has to have the consideration of draft. So you have to alter the initial design so you can even pull it out of the mold. That's old school. That's the way it used to be done. This is a core box from Schmidt, who now works for SpaceX. In 2000, he wanted to design a manifold. This manifold was specifically designed to operate up to 7,000 RPM and no higher. You notice the runner length is long.
Yeah.
And at the time, all the bracket racers, super gas racers, all these guys, they didn't want to turn their engines up, and they still don't, because engine speed is decreased TBO, time between overhauls. Yep. If you can turn an engine 7,000, you can run for years. If you turn it 8,000, you got to freshen it up every year or two. If you turn it 9,000, you got to freshen it up every year. And if you turn it 10, 11,000, you got to freshen up every 30 runs. So the higher the engine speed, the less time those components last, and you have to freshen the engine. So all these guys wanted 7,000, 7,500 max. So he tuned it to 7,000. The manifold really didn't sell that well because, well, it takes about 10 to 12 years for anything to catch on, and he built it for the time, which is what we always do. We can't predict the future. And the manifold runner just ended up being a little too long for most people, and they didn't want to operate the engine because at the time he make this manifold, the engine started getting bigger and bigger and winding higher and higher. So the manifold's place in the industry kind of got left behind, but it was an awesome design. One of the best I've ever seen for a cast single plane manifold. So what this dictates is the core. If you see in the upper right-hand corner, that's the sand core. That's what we call the spider core. That's solid sand. The aluminum is poured around that sand. So anything you see solid in that core box ends up being aluminum in the final product, or open. And the open ends up being, the sand ends up being the open part, the air. But with 3D printing of cores, those days are long gone. We don't have to worry about draft. We don't have to worry about pulling core, all that stuff. Nowadays, this is a water jacket core that has been 3D printed. And the point I want to make here, I wish people understood how amazing the thing I am looking at actually is. Do you see those thin little areas of sand? Yeah. Small little tiny passages? If you had a two-piece core box that had to be pulled apart, that would be impossible. There's no way to make that water jacket in any other way but 3D printed. And another thing is they're very fragile. I mean, these things are made out of sand and binder. So basically it's glue in sand that solidifies. So it's like glass. If you hit it, it just shatters. So pouring these, I don't know if anybody out here has ever heard of a floated water jacket core. Let's say you're porting on a cylinder head and this happens not so much anymore, not as much anymore, but it still happens. You get a new cylinder head somebody has designed. They say, give me an exhaust port. Inevitably, you choose the exhaust port where the water jacket core hasn't floated. And these water jackets are held down, okay? So as you pour the aluminum in, the aluminum is more dense than this casting, so it will float if it's not held down. So if any piece on that breaks, it floats up. And what that happens is, let's say you have an exhaust port, one end here and one end here. If that water jacket core floats up on this end, the floor is thinner. So you port this one, and then you go to port that one, and it breaks into the water jacket. And you're like, what the hell happened? We had a whole run of heads. I've seen whole runs of heads like that had snapped the pedestal on the water jacket core, and it floated up on one end. And you can't see that in the finished product. It's not, unless you saw it apart, you can't see it. So those days are fewer and far between, but they still happen. So let's look at 3D printed manifolds, single plane manifolds. The revolution. This is a revolution, by the way. It has changed everything. It has changed the harmonic we tune to. It has changed the VEs we can achieve and the RPM potential we can achieve. With a standard cast manifold versus a 3D printed custom design core, the RPM potential is up to 2,000 RPM higher. Because you cannot design the runners in a two-piece core box that comes apart in such a way that they're straight enough, they're angled correctly, everything works out to your design. You have to compensate for the process. This is a Dart manifold. And back in the early 90s, when this thing came out, it was revolutionary. It was like 30 to 40 horsepower. That's because the port efficiency was 75, 80%. The valves were smaller. The RPM range was less. So when this manifold came out, it was perfectly tuned to the engine combinations that were out in the wild. It actually helped them. Then we had higher lift cams, we had better cylinder heads, better ports, higher efficiencies, and all of a sudden this became a restriction. So what did we do? Well, we sawed the thing in half or in 4 pieces. We welded the runners up straight. We raised the carburetor 3 to 4 inches, and we put $65,000, $7,000 into these things in order to make them perform on the modern cylinder heads. We don't have to do that anymore. This is an SB2 manifold, and this is a cast manifold from a foundry, not 3D printed. Right. But you see that they started, see the difference between bending the runners around into the plenum versus standing the runners up, making them dead ass straight, which if you bend a runner, you're done. You're over. You have hurt the engine, period. The runner has to be dead straight. And this is another mistake. And the reason I harp on that so hard is I see it all the time. It's like people will design a manifold with curve. Those days are gone. If you have a port like this and you have to turn the corner, okay? If you try to bend that and make it aerodynamic and swoopy and make it look real nice, power goes down the tubes. If you make it straight and you can handle that one bend that you have to make, you can handle that one gradient. You can't handle a velocity and increasing gradient all the way to the manifold. That is unmanageable. So what they did is they made the things wider. They tried to increase the airspeed to pull the air around the corner. They did all this stuff to try to manage curved runners, which are death to VE. Anytime you curve a runner like that, it's easier to just make that bend, navigate that bend, make the area proportional to where you can turn the air there and be done with it. If you try to make the thing swoopy and make the thing turn, the air doesn't turn. It's going to initiate a gradient. It's going to break the boundary layer. It's going to go turbulent downstream. Make it absolutely harmonious. The velocity is actually increasing, then turn it when you need to or you have to. And this is SB2 manifolds from 2000. And as you see, they just elongated the plenum. So they killed a whole bunch of birds with one stone here. They got rid of the velocity gradient by making the runners straight. They increased the plenum volume to raise the power band. They raised the runners to increase the efficiency of the port. They did a lot of things here that increased power. I mean, you're talking engines that used to turn 8,500 now making power at 96. Just boom, within 4 or 5 years. But this is still a cast manifold, and it still has drawbacks. You still have the draft. You really can't get the end runners and everything exactly the way you want because you got to pull that spider core. So what you're looking at here is a simple experiment, a CFD, computational fluid dynamic simulation of a perfect velocity gradient coming into the manifold and then looking at how it gets disrupted by the shape downstream. So what you're looking at here is the velocity gradient. Red means the velocity is taking a dump. And then the blue is easier to look at pressure. High pressure, low pressure. So the low pressure, you've got low pressure, low pressure. But look at how even, the runners aren't that uneven. Okay? Mm-hmm. They're a little uneven, but the outers are suffering just a little bit, but the insides, that's all right. You can live with that. Now let's look at an absolute disaster. Now, in order to not affect it downstream, hold on a second, let me draw something.
Wow, guys, this is really blowing me away. I mean, I've never seen anything like this, and I'm just trying to absorb it. So I think you guys are too. We got 137 people here right now. So, Ken, you guys got a lot of questions. I see on the side. I just don't want to interrupt.
Those will both flow the same. This runner right here with this huge bowl stalls the air, and this one right here is efficient and turns the air efficiently. They'll both flow the same, even though the gradients and velocities are completely different. So by putting this huge square box up there, what you're basically doing is you're getting rid of a lot of the gradients and pressure differential before it enters. In other words, you're not trying to set up this perfect, it escapes me.
Not pressure gradient. You're not talking about that.
Convergence. You're not trying to set up this perfect convergence angle of the air all coming in homogeneously and increasing its velocity evenly. You're stalling the air and letting the manifold take what it wants. Okay, so all the gradients are just up here in this box, and the manifold basically takes what it wants. This is another way of doing CFD. And let's say that entrance was 6 feet away. So all the turbulence is going to somewhat become more laminar by the time it enters the manifold. And you can see what's going on as far as the natural pressure gradients within the manifold. But this still, you can see this one is still affecting it. If you notice the natural path, the blue path right through the middle, by the way, air doesn't like to turn. And this is an improper CFD analysis. Now, I wanted to show this because this is when you're working with simulators, you're thinking, I'm going to simulate this thing and I'm going to see what's going on. Do you see what's wrong with this? I'm going to take a short break. I want you to think about it. By the way, you need a radius anytime the air enters anything.
I wish I could point to it. I can see right what you're talking about. There's a bottleneck there. But anyways, guys, so it's kind of a deep subject. I mean, I'm trying to grasp my head around it. And I can see on here by the live chat, there's a lot of guys on here that explain or understand it probably better than I do. And I just can't put your question up here. I don't want to interrupt Darin and get off to side topics. You know, we've been talking for like almost 2 hours now. And I hope you understand. I just want to get his presentation out. And now that we have him here, we'll be able to get him back. You know, it's been a while. Like I said, it was a year on the 14th since we did a live chat. And we talk a lot. I shouldn't say we talk a lot. We text back and forth here and there. Questions, I'll send him port pictures or ask him a question about something.
The simulation is only as good as the person designing the simulation. If you notice, there's no entry radius into the plenum.
It's like a shoulder.
So you get a shear effect.
Yep.
So all the data downstream is worthless.
All right.
This whole simulation here, although this box right here is used in simulation, so you get all the gradients, the vortices, the non-laminar effects of the air entering the plenum out of the way before it enters the manifold, as opposed to setting it up like this. Basically, this is a divergent. The divergent angle of this right here slows the air down at a given rate to where you don't break the boundary layer like you see here. This is a breaking of the boundary layer, meaning the air has detached from the wall, the pressure is going nuts, and now you have vortices or vortex generation here, which is not good, but from what we do every day. Oh, by the way, look at the pressure. This is pressure, by the way. This is airspeed. This is velocity. This is pressure. Same thing, pressure.
So let me ask you,
what?
When I look at these pictures, what I see where the I don't know, not necessarily the convergent, but the limiting factor is right at the plenum, right where the carb is sitting, right where the air is coming down to turn. That's where it seems to be a stricture. Do you know what I'm saying? The shoulder, that area. Am I right?
Again, this is where CFD and the real world dynamics don't really match, because you have a carburetor on top of there.
Yeah.
So the air is actually being limited by the barrels. So you don't have a perfect velocity gradient going in there. So this is not mimicking real world condition. All you're trying to do is get rid of the problems before you bolt the carburetor on there, and then experience those problems to try to counteract those. This is a common issue. Anytime you put a throttle body out in front of a manifold and dump pressure before the front runner, you've got a game to play that I don't like playing. I mean, it's almost impossible to fix. You get either you get this huge gradient right here. It starves the front runner. There's no air. The air doesn't want to go in there. This is the worst case scenario, by the way. This is a simulation of what happens when you design it incorrectly. Because you see this manifold goes here and then goes out. What should happen is this should come out and keep going and keep going, and this should keep going. It's called a divergent nozzle. The divergence, the angle of that divergence entering that system, or the airspeed increasing, has to be just right to be able to turn the air into the system. And I was looking at the diesel guy. What is his damn name?
Banks?
Banks. Yes. All these diesels have these elbows.
I saw that. I saw that. Yeah.
They're the absolute worst thing I have ever seen. Every one I have seen was like, well, there's 20% power. I mean, it's just absolutely pathetic. And then they put a divider in the middle. It's like, what are you trying to do? You're trying to correct a problem, but you're doing it the wrong way. And then he looked at, obviously, CFD aerodynamic studies, and he came out with an elbow that was like, okay, yeah, that's it. This guy knows what he's doing. But you notice that all these runners have a different pressure at the opening. Every one of these things is different. So the signal from every runner is going to be different. So your air-fuel ratio in every cylinder is going to be different. And the number one cylinder is going to lean out, detonate, and blow the rings right out of the motor. This is the elbow. What happens with an elbow? Elbows, every time I see one, I just want to kick them in the dirt and hit them with a sledgehammer. Because this is an unwinnable, unfixable situation when you have to do this. If you look at the gradient, from the air has break the boundary layer even before it has to turn. It's breaking the boundary layer. What? The red is an inch before the turn, and it busted the boundary layer another inch in front of that. It's already. So now look what happens at the very back of that elbow. You see that blue? Mm-hmm. That's your flow zone. You have shut the entire flow zone of that nozzle down to about 1 inch. The rest is just vortex generation and turbulence. So the front two runners are detonation nightmares, and the back runner is supercharged. So the back runner is going to be 13-1, and the front runner is going to be 16-1 air fuel ratio.
Yeah.
There's the pressure that shows it. Now, the inertia supercharging effect of any intake manifold entrance is also very, very critical to how the engine runs. Pro stock engines nowadays with their front mounted, oh my God, that was a huge learning curve for those guys, because that thing would pressurize, it would instill a gradient and cause break the boundary layer and cause the front runner to go lean, but the inertia effect would ram charge the back cylinders. And then as the airspeed or the car speed increased and the airspeed in the manifold or the hood scoop increased, now the manifold's seeing a completely different pressure. And now it's ramming the middle of the runners. It's actually changing. Now, when we had carburetors, we had pressure sensors on those things. The back carburetor was jetted and air bleeded different than the front, because the front takes air, which drops the pressure. So the back carburetor was seeing less pressure by about 0.7 HG. So the jetting and air blades on the back carburetor would be different than the front carburetor. It's a situation that's always existed and probably always will and always has to be compensated for through tuning. That's why you can't tune a manifold and a plenum and carburetors on the dyno. That is an impossible task. I've never seen anybody do it. Every professional team I know that races carburetors had a set of dyno carburetors and a set of track carburetors. And you didn't get those mixed up because there's 20 horsepower difference between the two. This shows a too fast increasing divergent nozzle into the manifold. In other words, you're opening the area too fast. You can see the boundary layers breaking right up at the opening. Now, anytime you bust that boundary layer and instill turbulence in the system upstream, that carries downstream and it gets bigger. It doesn't correct itself. It gets worse. So the whole idea is not to get in that situation in the first place. Keep the airspeed high, keep it as uniform and as laminar. Laminar is kind of a misnomer. There's no such thing as laminar, but keep it as laminar as possible in the system before it gets into that plenum. When it dumps into the plenum, okay, we can manage that in a different way. But a converging area to the top is better than a diverging top in a manifold. Point in case, the question you were just asking me in the manifold sitting right behind you, you turned a 4150 manifold and put a 4500 adapter on it. So now you have a 4500 plenum and it has to open up to a 4500 carburetor. That's the best case scenario. That design has almost always made more torque and power on single plane manifolds of that type, because what you're doing is you're increasing the airspeed right to the apex to turn into the runners. So what you're doing is you're getting increased plenum volume with that spacer. You're getting the better ability to turn the air into the runners, and you're setting up a high pressure area over those boosters. So what's going on in the manifold isn't affecting the boosters as much. Oh, the elbow. This is kind of indicative of bending a runner. Anytime you have a runner going into a port and you try to bend that around a corner, try to make it all pretty and swoopy, this is what happens. This is what happens in a runner. This is what happens in any time you try to change direction of the air with an elbow or a bend. Yep. It's if the apex of that turn is right when the yellow starts. Do you see it?
Mm-hmm. Yep.
2-3 inches above that, you see the blue that has already busted that boundary layer. The air has detached from the surface. It has gone turbulent. Now look at the blue at the back of that bend. That's the flow zone. That is all the air that engine is getting. It has shut down that flow zone. Instead of having this much area to flow, it's got this much area. Instant VE hit, instant efficiency hit. The front runners go lean. They get detonation sensitive. You supercharge the back runners. Now you're trying to stagger jet this piece of crap. So you're trying to put bigger jets in the front and smaller in the back, or try to counteract it with porting or whatever. And sometimes you can increase the airspeed on the front runner and help it pull that air in, because it's already inefficient, right? This is where airspeed helps correct a lot of problems. So if it's inefficient and it's using less air because of the turbulence, you already know this, shrink it up, get the airspeed up. It's using less air, increase the efficiency. Boom, instant power. You can see that front runner is dead. Yep. Now, not only is it dead from a pressure aspect, from a turbulence aspect, from vortex generation, from, oh my God, it's horrible. Now, all that, once you instill turbulence upstream, that carries all the way downstream, and it just gets worse and worse. And by the time it hits the short side in the valve, it's worse than ever. So all your porting and perfect port design and all that stuff, it goes right out the window. Okay. Now we'll talk a little bit about inertia ramming. And a lot of front mount throttle bodies have this problem. This is a 4-cylinder engine. You can see the airspeed coming in through the throttle body, and the front runner is dead. The back runners are supercharged because the air doesn't want to turn. Air doesn't want to turn. It wants to go in a straight line. So that air velocity is really high, and it's going, and it wants to turn. It's like, nope, I'm going to keep going. And it shears off a little bit of it, and it just keeps going. So you've supercharged the back cylinders, and they're 12.5 to 1 air fuel ratio, and the front cylinders are 17. That's an unwinnable situation. Same thing goes for mounting it right in the middle. The problem here is you don't have a divergent angle coming into the plenum. So that square angle there at the top, instead of it being flat, it just coming straight into a flat, it should come in radius. It should drop the pressure at a given rate to control it. That's the whole idea here. I don't want to just dump the pressure. It's the same thing with the valve. When you open a valve, you don't want it to just open into nothingness. You need those walls real close to that valve to control the pressure drop. When you just open it into a plenum, the air does exactly what it wants to, which is go straight. And it's going to supercharge the center runners, and the outer runners are going to be lean. This is indicative of a 426 Hemi with a cross ram intake. Even though the carburetor's on top, it does the same thing. And that's it. Any questions?
Wow. Any questions? What are you trying to make me funny? I'm telling you, man, I'll go back through and look at some of the stuff. But like I was telling these guys when you were taking the break there, I mean, there's so much here. I'll probably go back. I won't watch it because the beginning was kind of rough on the internet with some lag and stuff and buffering. But I'll just put it on the garage and listen to it again, and look back at the pictures, because I have to hear this a couple times, because it's way past my pea brain when it comes to airflow. But I'm getting the concepts. I'm understanding what you're saying, which makes me when I look at that intake back there, I can't wait to get on it tomorrow, and start grinding, because I got ideas. But yeah, it's amazing. Let me see if I can get a couple questions.
With the manifold behind you, you have that 45 degree, you have a divergent or a convergent angle coming into the plenum, which is good. All the areas, now all you have to do is design the radius leading into the runner that's the most efficient as possible.
Yep.
That's the easiest
Not necessarily
situation.
Take the whole walls back. Not necessarily take the whole walls and make a huge plenum. Let's get the radius better.
Let's talk about runner angle for a second. I drew these up. So let's say you have a port, okay?
Yep.
The port's coming out and it reaches the flange. So the runner should just be a continuation of that port. You shouldn't change the angles. It should just be a continuation of those angles. That's not always possible. Now, like on a 23 degree, you have this. So now you have this huge gradient built right here and right here. So all the air is on the roof. Now it's a straight line. Here, I'll draw it for you. That's the airflow path. Regardless of how you bend it, that's the airflow path. That is the highest velocity in the system. So now what you've done is you made this area completely dead. You've made this area completely dead. You've made this area completely dead. You've destroyed the efficiency of the system. There is one way that we have found, and what I have had so many conversations with Foltz and Maskin and everybody on this topic, and we still don't know exactly why this works. But this is exactly opposite of what most people try to do. Most people try to do this shit. They try to stand the runner up more. And when you do that, all it does is make a little bit more top end power and kill the torque in the mid-range. But on all pro stock engines, that roof angle is laid down 2 degrees. And Foltz kind of brought up a deal. It's like the short side right here. That's the highest airspeed, localized airspeed in the system. That could be up to like 380, 400 feet per second. So by bending the runner down like 2 degrees, it takes the load. His theory was it takes the load off the short side. You actually have a bend. Now you can change air direction by 10, 15 degrees, and it's not going to see it. It's going to treat it as a radius of 10 or 15 degrees. So that 2 degrees is almost, the air does not notice that. But it takes just a little bit of load off that short side to where you can design the port with a little higher short side, a little more pressure drop, and pull the fuel around the corner. That's all I got.
Speaking of that, let's look at some questions, Darin. I'll start putting some questions up because guys wanted to ask, and I told them, listen, I can't ask them now. Let's wait till we get done. So here's one now. Let's see. Ken Mole. How critical is the entry angle at the head entry? Can 70-degree or 10-degree angle changes at the head affect fuel being dropped out of suspension? We already know that being efficient there matters.
Okay. Yes, in certain areas, no in others. In other words, if you're on the push rod wall that already has a gradient or already has a directional change,
yes.
So your port's already your port wall's already like this. So you can go ahead and bend it a little more, and you're not really going to hurt it that much. But let's say the high speed wall, what we call the bore center high speed wall, which is the roof and the wall that are parallel with bore center. If you put that angle in those areas, yes, it will most definitely hurt. Beyond any shadow of a doubt, 100%, it will hurt it. If you put it in the floor or the push rod wall, maybe, maybe not. Depends on the system.
I don't know if this helps. I wish I would have had it up here where we could point. I wish you could point with a cursor when we're talking.
I know. I do too.
You know what I mean? Well, I'll have to figure that part out. But I love looking at this head, when we talk like this.
Now, on a manifold on like that Cleveland head right there, you need to match the roof and match the high speed wall. And again, but with a single plane manifold, that's not possible. You always have to bend the runners in for that carburetor to try to get them underneath the bores a little bit. But you notice the 3D manifolds, the 3D printed manifolds nowadays, and I forgot to mention, the old manifolds were on the 4th or 3rd harmonic. The new manifolds are on the 2nd. It's like a tunnel ram manifold with one carburetor. When you bend those runners, you have no choice but to drop one harmonic, which means you drop energy, which means you drop VE. No choice, because the inefficiencies in the system. When you stand those suckers up, make them straight, you can put them on the 2nd, instantly increase VE.
Here's another one. Eric McMahon. Darin Morgan, when you lay back the short side on a shallow angle LS head, do you flow ball/pitted tube to determine this or is it trial or error by dyno testing? Okay.
You have designated a very specific head, meaning the LS heads, and I'm going to say LS7, not the LS1 or 6. So we'll take this scenario takes place in both the LS1, 6, 3, and 7. Okay, same scenario. What you have is a big valve, more valve area than the engine can use. Okay, so the airspeed at that point is too low to instill enough signal in the system to drop the pressure to move the air into the cylinder. So instead of using the throat, like in a racing engine, as the highest velocity area, they use the short side upstream. The short side is the pressure drop. So what happens when you take a 1, a 6, a 3, or a 7 head with a very what we call hypercritical short side? And when I say hypercritical, I mean any mistake is huge consequences. So this is your high speed area. It's also what governs the mass flow rate into the cylinder. So and you have to realize these engines only have 600 lift, 585 lift from the factory, which is a lot. I mean, that from a factory deal, 580, 560, that's a lot of lift, but it's still not enough lift to utilize the throat velocity. It's too slow. You have all this valve area in order to make the power up high, but you have no airspeed to fill the cylinder down low. So they put the airspeed at the short side. So what happens to all your power at 1500 to 3500, even 4500 RPM is governed by that short side layback. So if you lay it back, the engine won't even come on until 4500 RPM. You've killed everything underneath that because you don't have enough airspeed to fill the cylinder at that RPM. So you are dealing, just like a 23-degree cylinder head, you're dealing with a hypercritical short turn. I have seen guys work for weeks trying to develop perfect short turns and then go on to the CNC and the digitizing and the program for that port and be like 20,000 steps and be perfect coming over that short side. No mismatch in the programs. It has to be absolutely perfect in order to achieve repeatability on the manufactured cylinder heads. So if you go in the bowl and you CNC it, and then you come in here from the intake side and you CNC it, and there's a mismatch that you have to blend in, that could kill 10 CFM. Just boom. I mean, when I say hypercritical, I can't even. It's hypercritical. I mean, the shape of that, I have worked for days on that. Anytime you have the airspeed on the short side that high, it is very difficult to tune the system up to work for a street high performance engine that will operate through a wide range of RPM. Those engines are designed to make 550 horsepower, which is a lot of horsepower for a street engine that cruises its whole life at 1500 to 1800 RPM. 95% of the time that engine operates is going to be at 1500 to 2500 RPM. And that's where it has to pass EPA, it has to get good gas mileage, it has to have good mixture in the combustion chamber, good burn rate, so they can get those EPA numbers. Well, that short side is what's doing that. That's dropping the pressure and moving the air into the cylinder. So you lay that back and you radius it off, and now you have to raise the RPM range to a point where the airspeed is sufficient enough to fill the cylinder. And that's 4,500 to 5 grand. You instantly take the torque peak from 2 to 4,000. So yeah, what you're dealing with is probably one of the hardest things I've ever had to deal with, because there are so many varied combinations on the street with LS cylinder heads. And although their power potential, I can take an LS cylinder head, lay the short side back, make a nicely designed, pretty good port out of it, move 400, 410 CFM, and make 900, 950 horsepower. But that's from 65 to 8,500 RPM. That's where that port, the actual port volume cross-sectionally doesn't even have to increase. All that airspeed is right at the tip of that apex of that short turn. So when you lay it back, you kill the torque. So what are you going to do? How are you going to get that back? You're not. You have too much valve area. You're done. So LS1 cylinder heads are something I don't even want to deal with. I mean, they have a low valve angle. Their valve is like 10, 12 degrees. So you have this huge amount of turn. The short side is like stood way up so they can get the airspeed, spike that airspeed right there. And they only have to get the airspeed high enough for a 600, 550 lift camshaft. And then you stick a 650, 625, 650 lift camshaft in there. Now the airspeed's too high. So if you just lay it back just a little bit and drop the airspeed from 440, 450 down to about 350, 380, you're fine. But once you lay that sucker back and she drops below 350, you're done. You just killed like 1,000 RPM of torque. I mean, in other words, you raised your torque peak. Those ports are a real balance. And it's because of the initial design of the system with the high volume and the high pressure drop at the short side, being able to manipulate that whole design to operate at a different RPM range isn't hard, but when people want to still drive it on the street, that's a difficult proposition. You can't make a racing engine. Again, you only have 1,500 to 2,000 RPM. So let's say you've killed the airspeed, you put a 750 lift cam in this thing. You're going to spend it 8,500 RPM. Where's that 2,000 RPM going to occur? It's going to occur from 7,500 down to about 5,500. Again, basically 2,000 RPM. And then you have 5,000 or 500 RPM of over rev to shift to drop back down to the power peak or torque peak. I mean, so it's not hard to get power out of them because you have all the volume and cross-sectional area and port height and everything you need on the LS3, LS7 heads. But managing them on the street to try to make a lot of power in a lower RPM range is quite a challenge. But that short side radius, when I say hypercritical, I mean 2 degrees too much layback, or taking that from like a 1/2 inch to a 3/8 radius will just boom, raise the torque peak 1,000 instantly. That's very hard to navigate. So basically my advice is to never drop the airspeed, average airspeed across the apex of the short turn, right when it goes over, right at the apex. Don't drop it below 350. And I've never seen a head that really operated below 350. And don't exceed 380. So you're going to have a gradient across the top of that short side apex. You're going to be 420 on the high speed wall at bore center. And then you're going to drop to about 380 in the middle, and you're going to drop to about 300 to 280 where it goes around the push rod. The average of those numbers should not exceed 350, which is your test pressure, by the way, on the flinch. At 28 inches, 146 CFM per square inch of valve area, 350 feet per second, 28 inches are the same thing. So basically what you're trying to do is not exceed your test pressure. At 28 inches, okay, that's 350 feet per second. If you exceed 350 feet per second, that becomes a choke. Yep. Next question.
Here's what I want to ask you while we're on that topic. Yeah, I'm gonna cut that into a section and put that on one of the LS forums, you know, for information.
There is a
the question I had was,
what I'm about to say, you better not put on any LS forum. Okay. There is
all right, I won't.
An organization called the Cathedral Port Mafia. You probably never heard of them, have you?
Well, I haven't even heard who they are.
A group of people that think the Cathedral Port head is the best absolute port design that's ever been created.
Okay. Never heard of them.
And they're right for an engine that doesn't exceed 5,500 RPM.
Get it. Now, we'll talk about that later. The Remember we had talked about this, and I had asked you this before, and I recorded it, and I want to get a clarification. We had talked about the Cleveland because I'm a Cleveland guy. There's a lot of Cleveland guys on here. You said yourself the 219 valve is too big for that cylinder head.
Say that again. I'm sorry.
On the Cleveland 4-barrel head,
Okay.
you said the 2.19 valve is too big for that cylinder head. Do you remember saying that?
For what they were originally designed
actually,
for, yeah.
For what would actually make more power with a smaller valve.
They had too much valve area, too much port area, too low airspeed. So you're looking at the Boss 302 as a perfect example. You have a big 4-barrel head on a 302 cubic inch motor. Now, again, my whole job is to make those areas as fast and efficient within the range that engine is going to be designed for. So the area available, both valve and port, for a 302 should operate between 9 and 11,000 RPM on that 302.
Okay.
So when you're trying to operate at 65 to 85, it has no airspeed, and it's a dog down low. It just won't accelerate.
Right.
I mean, those heads are perfect for like a 420 cubic inches underneath those heads works really well from 65 to 85.
Will it make more power with a smaller valve?
If you're operating a lower RPM range, yes. Absolutely.
Okay.
If you're operating in the RPM range from 2 to 5,500 with a 6,500 over rev shift point, absolutely they will.
Yep.
If you're operating from 45, go ahead.
So meaning if you have a street car and you do a valve job on that and you decide to put in, let's say, a 215 or something smaller, it's going to benefit tremendously.
It would if you could accomplish. It would if you could accomplish that, but you can't because the bowl is already a certain size.
Okay.
So you can't put a smaller valve than what the bowl.
Got it.
You're stuck with that valve size. So what we do is we keep the short side apex as abrupt as possible and get that airspeed up, and then keep the throats as small as we possibly can. And as a matter of fact, it's beneficial to put a 200 on there, which makes the throat airspeed higher and the short side airspeed higher. Because here you have your short turn, okay? Now, when you put a bigger valve in, what happens? That short turn has to turn more. So now you're spiking the airspeed. So in that particular case, you're looking at like airspeed. It's like, how can I get the airspeed up in this system? And that's make the relative areas smaller to the valve to get the airspeed up. And go 45 degrees, lots of angles, lots of venturi, down to like 88% of the valve, and a short side velocity. Hopefully you could get it to 400 feet per second. Spike the shit out of it. Because air is like, okay, how does air pressure work? Storm systems move from high pressure to low pressure.
What is it? High, low, yeah.
Yeah, everything moves from high to low. It's the same thing. If you can increase the air speed at the throat, at the short side, the air upstream is going to want to move to that area faster.
Yep. Just like we were talking about earlier with waves.
Airspeed.
Yep.
I mean, my job is not to get the most air through a hole. My job is to manage the airspeeds. That's my job. Next question.
We're going to make a little appetizer out of that. All right.
How long have we been on?
David Reed. 2 hours and 29 minutes.
God, it feels like an hour.
I told my wife, I said, we may be 3 hours. I don't know. Probably not longer than that. Darin, Would you explain the cant on the short side floor? Why, how much, when?
This is not hard. If your valve is canted at 4 degrees, your floor should be canted at 4 degrees. Because that throat should be, if you've tuned the system correctly, the highest airspeed. The last thing you want to do is instill a velocity gradient at the short side, because if the valve is canted this way and you have a straight short side, the path between the two high velocity areas is different. That's a gradient. Cant it with the valve. The valve is canted like this, you cant the short side the exact angle. Now, there's a lot of discrepancy in this, and this is something that I'll give you my opinions on, but there are varying opinions on what I'm about to talk about. And that is, the valve is canted at 4. Should you cant the whole port at 4 degrees? And I say no, absolutely not. But there are heads that work exceptionally well that way. And the only reason I say not to do it is because it's hard enough if you have a port that comes in and your push rod wall goes out, okay? This is your gradient area. This is your pressure drop area. Every time that you have to go around that push rod. So if you're canting, the valve's canted like this, and you have a push rod wall that's straight, okay, this area is open. Now look what happens when you cant the valve. Now you're shutting off the roof over here. I would rather have a straight port and a canted valve and let it see that area on the bowl. And every time I do that, the velocity is higher on that side of the bowl. I decrease the gradient when I do that. So, but I will say that the runner coming out at the same cant can set the air up for that transition. So I've tried it both ways. I've always had a little better results with the port straight up than canted with the valve. The short side itself should always be canted at the exact valve angle as the valve. That's what I'll say.
Thank you. Carly Wolf, $10. Thank you.
Thanks, man.
Thanks for all your info. We appreciate you being here. Here's one that's from a buddy, Chris Palnick. If I needed to lengthen the runners on a tunnel ram, could I extend the runner into the plenum chamber? In other words, put a trumpet shape on the end of the runner.
That's what we call, what we used to call donuts. Basically, you have a flat plenum floor and you have the runner entrance at the floor. What you can do is you can continue that out and then come back down around. You can form this radius all the way around the runner. That does multiple things, none of which are bad. It's runner isolation is a primary component of being able to move the harmonic from the third to the second on 3D cast manifolds. What I mean is when all the runners come together into the plenum and you only have, they come to a point, you have no isolation between the runners. So all the harmonics and subharmonics act on each other. And it's quite a mess a lot of times. And this is another reason why you have to drop a harmonic. So when you move those runners apart and give them isolation, isolate them from each other, separation from each other, from any wall, including the outside wall. And in my opinion, this is a mistake everybody who prints 3D manifolds, and I hope people hear this, make. The outside runners just continue into the plenum when they should stop at the runner entrance and come out and isolate that sidewall, because you have the inside and the outside comes out longer. Okay, wherever this ends is the actual length of the runner. not here. So if you have isolation, in other words, come out around that runner, each runner works more independently instead of being reliant or affected by the runner next to it. So now it acts like a tunnel ram. And when you extend those or put donuts on them, a couple of things are going to happen. Your signal is instantly going to go up. Your low end torque is going to increase. Your mid range is going to increase. And if you're too short, the top end power is going to increase. If you're already at the proper length and you do that, the top end power will drop. And you'll see that in the BSFC numbers too. And when you look at an engine, when you're trying to diagnose a manifold, with carburetors, it was pretty easy because you could just look at the fuel numbers, look at the fuel curve and look at the BSFCs, look at its efficiency, BSFCs, brake specific fuel consumption. That is an efficiency number. That's how much fuel you're using to produce the power you're making. So if your BSFCs at the top of the RPM range or going into peak power and coming out of peak power start going up, meaning at peak torque you had 0.39 brake specific, in the mid-range you had 0.4, 0.42, and all of a sudden you have 0.45, 0.46, 0.47 at peak power and going, the system is going inefficient at that point. It's not utilizing the fuel you're giving it to make power. So then you have to ask yourself a question. Is it too long? Do I not have enough taper? Or other things. So that is a primary indicator. But with EFI, you can kind of band-aid all that. You can finesse those fuel flow numbers and really not see that. And that's where carburetors were a huge indicator to us. If you put, and there's still pro stock engine builders that will dyno the engine with carburetors because we're used to looking at the fuel curve. The fuel curve is the lifeblood of the engine. That is what we diagnosed everything off of, from Glidden to everybody. We looked at it. If the fuel flow, let's say you made a change to the system. Oh, here's a perfect example. If you have two engines, and one engine's using 530 pounds an hour and making 1,300 horse, and the other engine's using 520 and making 1,300 horsepower. The engine flowing 530, we used to say that's not choking on the fuel. In other words, it's able to move that fuel through the engine and still make the same power. What that means is I can load the engine harder. If it's moving more fuel and making the same power, I can load that engine harder and go faster. Every time. It was. So if you do, whatever you do to a plenum and a manifold, look at the BSFC numbers, look at the fuel flow numbers. If you're on an EFI system, look at how much you have to increase or decrease the fuel flow in those particular areas. If you have to increase the fuel to make the same amount of power, red flag. Think about it. Stop. Whoa, what am I doing? I'm trying to shove the fuel into this engine that doesn't want to take it. Or maybe it does want to take it. So let's take two engines. One engine's moving 520, one's moving 530. I jet this sucker up and it moves 540 and only drops 5. I jet the other one up to 530 and it drops 15. Well, that just tells me right there that the one that's moving fuel and not choking on it is going to be loaded harder and accelerate down the racetrack harder. It is that simple. Pay attention to your efficiency numbers. How efficient? What happens to the efficiency? The BSFCs, if they start skyrocketing, you need to stop and think, what am I doing? Even if the power's better, because you can lean an engine out on the dyno and make more power. But leaning an engine out gives it less fuel. Fuel is power. The more fuel you can flow, the more power you can make in a loaded condition. Don't lean it out, because on the dyno, you're set at 600 or 500 or 300 RPMs per second. You lean it out, get the burn rate up, the dyno compensates. And this is why we had dyno carburetors and race carburetors, because it's two different tuning worlds. But, and I have to say, Bob is the one that taught me that. Fuel flow is load and power. An engine that doesn't choke on that fuel is going to go faster. So if you put those donuts in the manifold and the BFCs go up, you went the wrong direction.
There you go, Chris. Thank you. George Dreesh, at what point does valve lift max out a given throat?
Those two aspects don't directly correlate with each other. There's no distinction that I can draw between max lift and throat without having an engine combination stated completely and mathematically in front of me, because those are two variables that are tuned outside of each other. The max lift and a given throat. Okay, well, let's say you have a street engine that doesn't see the high side of 7,000. You're going to have a throat of no higher than 90%. But valve lift is not proportional to your throat size in any way, because you can accelerate the valve and get it into a higher lift area at max piston speed, not change your throat, and achieve more power. But it all depends on the combination, what you're trying to do. But those two areas are not directly correlated with each other. In other words, you can affect one, and it's not exactly, it depends on the combination. It really does. And what you're trying to do with the engine. Let me think of a scenario. Let's say you're trying to turn 12,000 RPM with a 350 cubic inch motor. Your throats are going to be as big as possible to capitalize on the air flow potential of the cylinder head and the potential of the valve. And the valve lift is going to be proportional to how much I want to try and surpass that limit. So if the valve can only flow enough air on that engine size to attain 10,000 RPM, and I want to hit 11, at that point, I have to accelerate the valve faster, and I have to lift it further when max piston speed at 76 degrees top, or 76 degrees after TDC is achieved, to expose a larger flow area. But the throat is not correlated with the lift.
It sounds like valve loft. Like
that's a whole other
playing an effect there. Yeah, I know. I love that. Here's one. Let's see. Suicidal racing. How much power is it worth to use 30 thousandths offset dowels on LS3 heads on a 4-inch bore?
Depending on what you're trying to achieve, whether it's a road race engine, a street engine, or a high performance engine that you're trying to squeeze everything. Let's just take the scenario that you're trying to squeeze every bit of efficiency out of that system you can. You've got 965 gross lift. You're trying to turn this thing 9,200. You're just trying to get that last bit of airflow and efficiency out of the system. It'd be worth about 15 horse. On a street engine, you wouldn't even see it.
Would it change any difference if you moved it 60 thousandths to center it more in the
Yes,
bore?
at that point, on a street engine, you probably still wouldn't see it with 585 lift, but you'd probably gain 25 horsepower at 75, 8,000 RPM.
All right, Ben Alameda, you heard that. Let's see, next question.
And I have taken, there was a class called Mexican Pro Stock. And in Mexico, they had a Pro Stock class. And this class was 468 cubic inches, stock block, stock heads, and Brodix had a spec head. It's the spec head everybody knows. It has spec in the floor. cast into the runner
Okay.
itself. You can't touch it. You can't do anything to it. You can't port it. You can't do anything. I mean, this spec is in the roof and the floor. You can't touch the dang thing. So at the time, there was no rule against offsetting dowels. So what we did on the big block Chevy head is we offset 100 thousandths this way and welded up the exhaust side, and then offset 100 thousandths back, which let us carry the chamber out further. That was 35 horse, doing nothing else but that.
Yeah.
Of course, that took about $6,500 to accomplish.
See if there's anything else we need to finish up while we're here. So many guys ask questions. It's hard to go back on this and find out who asked what and do an organized fashion. We should almost just do a live chat, Darin, where we just sit here and BS and let people ask questions and let it roll like that. You know, it's fun just to hear the answers that you're given. Although some of it doesn't relate to me, I still pick something out of it. You know,
let's
do that.
We can do that.
All right, you want to do it?
Yeah.
Hell yeah, let's do it. What do you guys think? You put in the comments here if you want us to do a live chat where we'll just put on the camera and hopefully the internet's better, and we'll sit here and we'll just start doing firing questions and answers and just do a BS session. You know, you're into that, right?
Yeah, absolutely.
All right. Okay. Let's see.
I shoot from the hip. I've never put something together like this and then rehearsed it. I just shoot from the hip. So
nope, I know exactly what you're saying. I try to, something like we talked about. Sometimes you can't plan things out. Like I said, well, we're going to start doing this. Let me do some shout outs and just talk, and I'll do this and that. I can't tell you anything. I just do it. It just comes out.
I put this presentation together at 6 a.m. this morning, from 6 to 12.
I was training. We were training our dog. We took him back to the trainer for the kids to learn how to do some training. We all had to get up early. So I know they're in there waiting for me to come in and give them a kiss goodnight for bed. So that's what we're going to do. We're going to finish it up here, 2 hours and 47 minutes, because I know you could talk for another 5 or 6 hours because you've done it before. So I'm not going to keep us doing that. But I want to appreciate everybody that's been here. Right now there's 127 guys here, maybe gals. I saw a couple women in here that are into racing. So that's a big crowd for a live chat. Now I put this on replay because a lot of guys can't make it, and we'll just see. The comments will start going crazy. And it's hard to keep up with answering all the comments because I try to answer every one of them. So if you guys really have a question in the comments section for this, put it down, and like I told Warren Johnson, I'll write him down. I've got half of his done, and he's going to come back on, and he just wants to sit and answer questions. So it'll be a kind of a fun chat. No, you won't have to plan for it at all because you already have all the knowledge in you. So we'll do that hopefully within the next, I don't know. It's hard to put a pinpointed date because you got your schedules, I got mine. So it's the roll of the dice. When it happens, it happens. Hey, you want to do a live? Yeah, let's do it. So we try to do that. So let's do this. We're going to end it now, Darin. I appreciate you being here and taking time from your family. And my family's waiting. So guys, stay tuned to DragBoss Garage. Make sure you subscribe to the channel, because all these people here, I want to see some subscriptions, because that's how I'm going to get this channel built. Because we're going to save racing history for an archive where you can always go back. And the technical, I put a whole playlist on nothing but cylinder heads and flow dynamics. I've been taking up the live chats, cutting them into sections, putting in the important parts, and something like this. I can see already a couple of nice videos coming from here. Appetizers, I call them. So stay tuned to DragBoss Garage. We're always seeing.